Ok, professor.
Okay, let's start. Good morning to everyone. It is with a great pleasure that I officially open the third symposium in comparative biology carried out by the postgraduate program in comparative biology, based in our Faculty of Philosophy, Science and Letters at Ribeirão Preto. Activity has been conducted since 2016 with the aim of being a facilitator of international exchanges. Communication in English, all the activities are conducted in this language. Also, it's an opportunity to show to ourselves, both students and advisor, what kind of research we conduct in our program. This event provides a meeting point for our students who can thus exchange experience in their research and interact with their colleagues. In the first two editions, the lectures were given by advisors of the program, by our postdocs, and by students who have done internships abroad. However, due to the COVID pandemic, this year's symposium will be fully online. Despite the limited human contact, this virtual format allowed us to invite researchers that are based in other countries to be able to offer lectures in their fields of activity, enriching this way the event. The event will count with three researchers: Professor Chabel Nino Elhan from the Federal University of Bahia, Professor Paul Fine from Berkeley University, California, USA, and Professor Jonathan Codd from the University of Manchester, United Kingdom. Each of these researchers have been nominated by advisors of our program, and they represent the main lines of research we currently have in our program: the evolution of biodiversity, ecology and biodiversity conservation, and finally, line of research in history, philosophy, and science, teaching and evolution. In addition to these lectures given by our guests, there will be two sections of lectures. One of them given by students that took part in activities of internships abroad, and they will be given tomorrow, and another section with talks given by our postdocs who are granted by CAPES agents. These talks, both given by our postdocs and our students, are important to show the research they've done. And in the case of the students who present their activities abroad, it may act as a stimulus to other students to do the same. Finally, this year, the symposium features a virtual section of short videos. These videos were previously made by our students showing the research they are conducting in the post-graduation. We propose to the students to make their videos with an accessible language aiming at scientific dissemination to a wider audience. These videos were uploaded to the Comparative Biology channel, that is where most people are watching this ceremony in YouTube. And we hope the material produced by our students be of interest of the program, but also to a wider audience outside the academy. First of all, I'd like to thank the board that we have here of representatives of our university, including Professor Carlos Gilberto Carlotti Jr., that is our Dean of Postgraduation in the University of São Paulo, that will give us a speech later. Professor John Campbell McNamara, that is Vice Director of our unity, and this is special to me and to our program because Professor John McNamara is from our department, and he was one of our advisors, and he the co-founder of the program, and I think in 3 times he was the coordinator of the program as well. And I would like to thank the presence of Professor Cristi Leite Panisi, President of the Postgrad Committee of our faculty. She is the coordinator of the programs of graduation in your unity. Professor John McNamara, please, could you give us a few words?
Thank you, Milton. Good morning, folks, and a warm welcome to you all, and especially to our invited guests. I'd like to take a moment now just to acknowledge our university authorities. Roberto Carlotti Jr., who is our Dean of Postgraduate Studies at the University of São Paulo. Professor Christy Leite Panisi, President of our Faculty Postgraduate Commission. Dr. Milton Gropper Jr., the current coordinator of our program in Comparative Biology. Members of the Program Coordinating Commission, members of the Organizing Committee, and our invited guests, whom Milton has already mentioned, but I'll mention again. Dr. Charbel Ninho Elhani from the Federal University of Bahia in Brazil, Professor Paul Fine from the University of California at Berkeley, United States of America, and Dr. Jonathan Codd from the University of Manchester in the United Kingdom of Great Britain. And obviously to new supervisors or advisors, as some say, and student members of the program who are participating in this event. Thanks for this opportunity to take part in the opening ceremony of this third Symposium on Comparative Biology. I'd like to say a few words about the history of the postgraduate program in Comparative Biology, and particularly so since I've been involved with the program since its conception, as Milton has mentioned. This program began in 1997, which is nearly 25 years ago now, a quarter of a century. And its primary mission at that time was to allow faculty members in the Department of Biology to supervise the department's potential graduate students, which many of us were unable to do. Previously, departmental members and their students had to seek accreditation as advisors or to enroll in postgraduate programs in other faculties and in other universities to be able to develop their studies in their preferred areas of interest. And just as a personal example, while I was working here in Ribeirão Preto, I did for nearly 10 years in the physiology program with the Biosciences Institute in São Paulo, while we were establishing the present program in comparative biology. Now, little by little, over the intervening years since its inception, the program's focus has evolved from a generalist catch-all utilitarian program to meet the demands of our society, our university, student expectations, employment on the job market, and perhaps to a lesser degree, lines, but mainly we have adjusted our program according to our advisors' diverse interests in comparative biology, as you'll see during this symposium. And I'm sure Professor Carlotti will be talking a little bit about the university's aims as regards postgraduate studies and internationalization. So currently, the faculty members and students in the program now specialize in three overlapping and interdisciplinary areas. And these are evolutionary history and adaptation, ecology and conservation of biological diversity, and history, philosophy, and education in ecology and evolution. A moment to commend the organizing committee of the symposium for their work. And I understand that the committee is made up mainly of student members, so congratulations to all of you. And of course to our program secretary, Vera De Luca. Now I've looked carefully at the program and it's excellent in scope in my opinion, and importantly, it's the presentations from our invited guests. It includes talks from current students and from postdoctoral investigators who hold scholarships with the program. Now this is really important for these students and postdocs to have this experience, to talk in English, as mentioned, and also to be able to organize a symposium. This is good learning practice. So I'm sure we'll learn a lot during the symposium and have a great time exchanging new ideas over the next 2 days. And Milton, then, thanks again for the opportunity to take part in this opening ceremony, and a good morning to all you folks. That's it, Milton. Thank you.
Thank you, John, for your speech. It was a pleasure to us. You are here representing our faculty, and also because you are so important to our program in all these days. the foundation of the program. Thank you very much.
You're welcome.
I'd like to pass the floor to Professor Christie as a president of the Committee of Post-Graduation of our faculty. Please, Professor Christie, thank you very much.
Thank you. Thank you, Professor Milton, for introducing me. Good morning, everyone, especially Professor John and Professor Carlotti, Post-Graduation Dean of the University of São Paulo. I am so glad to be here in the opening session of the Comparative Biology Symposium. Also, I'd like to say some words before we start. I'd like you to know that this symposium is a great opportunity to listen to researchers from different places and assigned teams in education biology. It is the 3rd edition, and I wish that this initiative continues in the coming years. I hope we can have a fruitful times in the following days. I would like to thank you for this opportunity, Milton. Thank you, and welcome everyone. Thank you, Milton.
Thank you, Christy, for your words. We have a lot of work to do in the coordination of the committee of the post-graduation of our faculty at times of craziness of our governmental agencies and other stuff. So thank you very much for your presence and your speech, very kind. I hope so that the symposium will be repeated over the years. Thank you very much. Before I pass the floor to Professor Carlotti, I'd like to also thank our organizing committee, formed by myself, our vice coordinator, Professor Tomás Domingues, our postdocs, Dr. Danilo Trabuco Amaral, André Esguícero, and Dr. Ludmila Panzarin, and the student representatives Ariadne Delacqua, Iris, and Ana Paula Cipriano that is in this room. And of course, a special gratitude to our very efficient and super secretary, Vera Cássia Cicilline de Luca, always present and wanting to help. I would like to special thank you for having arranged all the dynamics of our YouTube transmission today. Behind the cameras, and Andrés also for organizing our book of abstracts. This is the first time we organized a book of abstracts to this symposium, and I think this is important also to the event. Well, I hope you enjoy the symposium these 2 days and that everything goes well for all of us. Stay healthy, stay safe. Now, it's everything all right, Professor Carlotti? To your presentation?
Good morning, everyone. I will share my presentation. Just a second, please. Is that okay, Milton? Is it possible to see my presentation?
Yes, that's perfect.
Okay. Good morning, everyone. I would like to congratulate the organization of the event for the quality of the program. It's a pleasure to talk to comparative biology program community again. I guess it's my 2nd year. I will comment some important points in relation to the activities of the graduate office of University of São Paulo, mainly for the current students and also for the future ones. Just a second. Okay. USP Graduate Program is considered to be of quality and has the largest number of programs among Brazilian universities, with more than 220 PhD programs. Graduate studies at the University of São Paulo have several areas of knowledge, allowing for an important interdisciplinary, I guess it's something wrong. Oh, it's okay. Interdisciplinary and complementarity of knowledge. Therefore, I encourage students to seek this knowledge with the participation of their supervisors in the various research spaces of the university. Explore all the possibilities of adding knowledge to their research. This environment can hardly be found in other universities. Another important factor in the quality of our supervisors, USP is one of the few Brazilian universities that almost all of its professors participate in graduate studies, most of them with postdoctoral degrees abroad. Regarding internationalization, we have two important programs supported by CAPES and FAPESP. And we can guarantee in recent years that all the students who want to do an internship abroad will be approved. When the pandemic has improved, we will certainly have this international mobility again. So pay attention. I assure the students they can be having scholarships abroad if they pay attention with PRINT, USP, CAPES program, and also BEP, FAPESP program. Regarding another important initiative is the English language courses in USP graduate studies. About 150 courses are offered each semester, so students can have the international experience in our academic environments. The Alcani Agents has maintained online language courses and also classes for scientific writing in English. These initiatives need to be better used by the students. We have many opportunities and we have many places to do this foreign language course. So you should visit Alcani website to see all the opportunities. Currently, USP has about 1,000 scholarships from CAPES, CNPq, and FAPESP. It's a significant number, but it's still insufficient for our students. It's important that each program seeks strategies to increase the number of scholarships. I understand that FAPESP is our best option to obtain a larger number of scholarships. In recent years, we have encouraged our supervisors to seek partnerships outside universities, in companies and government agents. Students' internships in these situations are allowed. An important point at this moment is the effect of the COVID-19 on teaching and research at the university. Right at the beginning of the pandemic, we transitioned from face-to-face to remote education. We are able to teach 2,400 subjects each semester during the pandemic period. The thesis and dissertations defense were also carried out remotely, and we managed to accomplish 73% of the expected numbers for the year 2020. The lab work has the most affected, so we made an extension of the deadlines for the students for 1 year. We are currently considering increasing the period for more 6 months. And we must highlight that USP researchers carry out different actions during the pandemic, with innovative research including artificial ventilators and an important presence in patient care. This is an example of the disciplines offered in English that are part of the Janus system. There is a specific place for these disciplines to be found. So if you follow my mouse, discipline in English, you can find in your Janus system, and you have a lot of disciplines in English in each semester. And just a second. Okay. Regarding quality, regarding quality, this graph shows showed that after many years below the other world average, USP surpassed this mark. Since 2013, USP has had the impact of its publication above its average. We needed to maintain and even increase the impact of our publications, but we should celebrate this performance. So during many years, we are below the average. In 2013, we crossed this line, and now, and it's maintained in the next years, we are above the average, the world average of impact citation. The number of defenses at USP reached closer to 7,000 per year, having remained stable in the recent years. This fact should be maintained in the coming years, and the focus of our work must be the quality of the training of our students and our research, and not only the numbers of master and PhD titles. The stability of the number of supervisors in graduate school explain and justify the stability in the numbers of defense. The CAPS evaluation of our programs has been very positive, with 70% having evaluation of excellent, so 5, 6, or 7. The programs with concepts 3 and 4 are mostly young programs, which will be certainly reach the concept of excellent in the next evaluations. This figure represents the areas of USP Print Internationalization Program. I encourage students to visit the web page and learn about all the possibilities of international mobility that will be available in coming years, of course, after the pandemic period. I recommend that you pay attention also to all possibilities of interaction with society, collaborating, for example, with scientific dissemination in form of the short videos for social media and also television. USP is proud of their graduate students. In this figure, you can find a former president of the Republic, a former governor of Bahia, and 2 ministers of the Federal Supreme Court, as well as internationally researchers, very known international research. The teamwork in graduate office is very small, but very active and willing to receive you whenever possible. So thank you very much.
Okay. Thank you. Thank you, Professor Carlotti, for your speech.
I close my presentation. That's okay, Milton.
Very much for your speech. It's always good to see the big picture of the graduate system, postgraduate system, maintained by the University of São Paulo, and see the importance of the USP or USP. It's strange to say USP. USP information of the new researchers and the teaching staff here in our country. We have data from our graduates, for example, in our program that show that close to 60% of the graduates in doctoral degree, we have still contacted with them, and they have established research groups at universities here in Brazil and outside Brazil. And we know the effort of this of you with the internationalization of the USP even more. If I may ask a question, I know that USP has the alumni system, as you told us, that is fed with data from US graduates. It's a question of mine. Is there any estimate of how many of our students go outside Brazil and settle there? I ask you because we know that nowadays we have difficulties in budgeting for research with cuts in the CNPq and CAPES as well. And I myself and my colleagues are concerned with the so-called brain drain. Is there any estimate of the occurrence of this fact, the brain drain of the students here in Brazil, or at least in USP graduates? Thank you very much.
Milton, we made a survey last year considering the students that graduate in the last 10 years in University of São Paulo. Only 3% of these students were in Europe or United States or abroad Brazil. So it's a small number, consider the total number. But I'm not sure if they are the best that they should be here and not in the Europe or United States. But this number is not so important. But I guess the quality of these students, they are probably the best one. So they should be here. That's my concern. So the number is not great, is not important, but I'm concerned about the quality of these students.
So only 3% of our graduates are settled outside Brazil?
Yes, in the last 10 years. Of course, the survey didn't look at all the students, only the ones that responded our survey. But I estimate about 3%. That's the number we have. Okay.
I don't know if there are questions in the chat. Maybe Danilo Ariadne could help us with this.
And I have no information about the next president of CAPES. I know that
terrible.
Everybody is worried about the point, but I don't have the name of the next president.
We are concerned about the Sucupira report these days because we don't know if it will be postponed again. I really hope that it will be postponed because we are full of things to be done, and all the scenarios that we have are very confusing in CAPES and also in CNPq. And I think 1 month more will be very good to perform a good Sucupira report to our programs.
Milton, the last information I have that will be postponed for 1 month.
1 month, it's official.
Yeah, but I'm not sure about this information. So I recommend that we respect the 23 of April as our goal to finish our job. But maybe we'll be postponed for 1 month. But you know, we never can trust in the Brazilia's information.
Okay. Yeah, we are really concerned about that. I don't know if you, Professor Christie or Professor John, would ask you anything to Professor Carlotti, because we have 5 minutes to the next.
Well, yeah, my major concern, of course, is the firing of the president of CAPES. Our government really doesn't seem to be very concerned about education at all, and firing someone like the president of the Federal Postgraduate Overseeing Board is a very serious measure indeed. And it's more surprising that our dean has not been informed of who the next president will be. I would have imagined that the US São Paulo would have had an opinion about who this person should be, Professor Carlos. We're the biggest university in Brazil, and I think we should have a say in who runs postgraduate studies on a federal level. Do they ask the University of São Paulo for their opinions on who should be the president of CAPES or who should be the director of the evaluation committee?
No, I can't talk in public, John. Everything I am feeling in this moment, but I am very disappointed with the situation because you changed the president of CAPES in the last minute of the evaluation. Everybody is very worried, and you changed the president without any concern about what it means to the universities, what it means with the national system of graduate studies. And so I feel that CAPES, it's a small agency that you can change, you can do everything you want, but I'm very disappointed, John. Yesterday or the day before yesterday, I told the Journal of USP what I think about this situation, and I hope that we can fix this situation in the next month or in the next years, because it was very hard to build a national system of graduate studies, and we can't put it on risk that in 1 year, in a few months, you change everything, you destroy everything that you built in 60 or 70 years. So we should be more respected the system, respect the university, respect the students, and not do whatever you want, and in 1 minute you change all the situation. So I say that I'm very disappointed, John.
Okay. Yeah, well, our budget, or not our budget, but the budget for CAPES is very small. But nevertheless, it's a very, very important agency on the federal level. And since it regulates all postgraduate studies on a national level, it does a tremendous job. It's tremendously efficient, even with that tiny budget, which is being cut even as we speak. I suspect that the new president of CAPES will also be making budget reductions. So we're probably in for a bad time, over the next year or so.
Yeah, you are right, John. 6 years ago, the budget of CAPES was 7 billion of reais. Now is 3.5, 3.6. So it's half of the budget of 6 years ago. And the system has increased during this time. So we have our scholarships, the amount of our scholarship, I don't know how to say in English, o valor da bolsa, the scholarship.
Yeah, the value of the scholarship.
Yeah, the value of the scholarship is the same of 80 years ago. In the last 80 years, there is no increase of the value of the scholarship. So it's a big problem, The system is increasing, the money is decreasing, and the result will not be very good in the next year. So I'm very concerned about the federal budget of science, education, and so on. Not only CAPES, but CNPq also. The budget of CNPq is 1.3, 1.5 billions. Is less than FAPESP. And FAPESP is only for the state of São Paulo. CNPq is for the entire Brazil. Is less than FAPESP. So we are very worried about the CAPES and CNPq.
Yeah, well, if we look at CAPES, as I recall, it's an agency within the Ministry of Education. and the education budget has also been cut. So that's going to reflect right across the board in all the regulatory agencies at undergraduate level, postgraduate level, and secondary school teaching and so on. I guess if we look at the real per student, per postgraduate student, this must have fallen drastically over the last 6 years.
Yeah, you're right.
You were mentioning the stipend, the value of the scholarship. So if we look at the number of AIs per student, since the number of students has increased and the budget is decreasing, that index must be dropping off terribly. Yeah, so I guess we're not starting the symposium on a happy note. I hope our research and our science will be more encouraging, and I'm sure it will be.
Yeah, let's focus in our job, in our research, in our students, and do our best. That's what we have to do. And USP has a very good position in the national system, and all the system look at the USP if you're doing right. So let's do our best. That's my main recommendation. I know you are following this goal.
Well, thanks for that encouragement. So, Milton, that's all I've got to say.
Okay, thank you, John. Christy, you raised your hand?
Yes. Thank you so much, Professor Carlotti, to be here with us and for presenting your graduation studies. It's impressive that your university continues its activity despite the pandemic. I would like to thank you, the Provost, for conducting the activities during this critical period. Thank you so much.
Thank you, Christy, for your help also.
Okay, Professor Carlotti, thank you for your speech. It was very elucidative to the main efforts of the university to the internationalization, to give grants to the students, and all the stuff and things that the university has been done these years to provide ways to the students to go abroad and complement their formation in their skills in the post-graduation system. Well, we anticipate your speech. If you want to leave, because I know that you are extremely busy and you have to dedicate your time to your multiple tasks in the dean of the university. So, of course, you are invited to see the next of the symposium anytime, because this day. But I know that you are a very busy man, and thank you very much for your presence here. And Professor,
I thank you, Milton. I will call Brasilia to have any information about CAPES, John. See you guys. Thank you very much, and congratulations for the symposium. Thank you very much.
Yeah, Milton, I have to leave as well. I have a meeting with Christy in another room, so I guess we'll be taking off. But I'd just like to leave a word of encouragement for everyone who is taking part in the symposium. I think our horizons are fairly bleak, but if we focus on what we have to do, like Professor Carlotti said, we'll get through it. So have a good symposium, and I'll try and drop by when I can during the afternoon during the talks. Thanks again for the opportunity.
Thank you, John. Thank you very much. Thank you, Christy. Thank you very much as well. Bye-bye.
Bye-bye.
Well, I think that the Professor Carlotti lecture was extremely important, Carlotti, because we could see the size of the importance of the USP or USP graduate system in our country, both in the numbers of people trained and the people that are trained in teaching skills and also in the research skills. We know that people who leave USP as graduates are often able to establish new research groups at different institutions in Brazil and abroad, being leaders in their fields of actuation. Okay. Well, it's time to the next speech, and the next speech is mine. I will present a little bit the program to ourselves, and after this speech, will be the presence of Professor Shabel Nino Elhani, and after a lunch break. I've forgotten to say that we have the videos in our channel, so I ask you to like the videos, to see the videos, and I've forgotten to say that we have a session of video awards in the closer section of the symposium tomorrow, and the videos, best videos, they were voted. We have the votes already, and the best videos will be awarded with some gifts. It'll be fun to see how the stuff that is going to be seen tomorrow. Well, now I would like to let's see my papers here. Sorry. I would like to lecture a little bit about our program and its particularities. Some of them you know already, but some of them are novelties. Share my screen. And I only ask someone in this room to say that's everything okay. Uh-oh, this is the final of the presentation. Are you able to see my screen?
Yeah.
Yeah, thank you. Who said that, please?
Ariadne.
Thank you, Ariadne. So now I would like to thank everybody again, and I will talk a little bit about our program and its particularities. And explain why our program is so special in the area of biodiversity here in Brazil. Because of the characters of our program, we choose the title Multiple Views. In fact, in spite of the program's main thread being the study of biological evolution and, of course, biodiversity, there's a range of possibilities for students in these fields in the biology. So, first of all, I would like to talk about diverse countries. The term mega diverse country refers to any one of the groups of nations that harbor the majority of Earth's species and high number of endemic species as well. The Conservation International, and I think that everybody knows what is the Conservation International, identified 17 mega diverse countries in 1990. Many of these countries are located in or partially in tropical or subtropical regions. Megadiverse means exhibiting great biodiversity. The main criterion for mega diverse countries is the high number of endemic species, genera, and families. A mega diverse countries must have at least 5,000 species of endemic, both plants or animals. And another criterion is that these countries must border marine ecosystems. So we have majority of the countries are located in the equatorial and subtropical and subtropical, in the equatorial and subtropical and tropical environments. For example, Congo, the Indonesia, Philippines, Papua New Guinea, Brazil, of course, our neighbors here, but some of them are in subtropical regions like United States, China, India, and portion of India, Mexico, and so on. So this is the 17 megadiverse countries in the world. In South America, we have 5 of these megadiverse countries. 5 of these megadiverse countries are located in South America. 4 of these countries are in the equatorial belt. That's nearly here, this mark. And it is influenced by the presence of the Andes. main mountain chain, like Venezuela, Colombia, Ecuador, and Peru. The recent uplift of the Andes makes the region of the Andes one of the most diverse in the world, with the mountain range housing diverse environments and acting as a species bomb, for both plants and animals. And we have endemic species that occurs only in these countries or even only in South America, the guanaco, the cuy, the spectable bear, the condor, and always and all other animals that occur only in these regions of the world. So the high rate of endemicity is characteristic of a mega diverse country. And of course, Brazil is also a mega diverse country due to its territorial extension and location close to the equator. It's the last mega diverse country that I mentioned in this speech. This territorial extension is home to several biomes, which includes the Amazonia, like this one, the Amazonia, the wetlands of Pantanal, the Atlantic rainforest, the Brazilian savanna that we call the Cerrado, the Pampas in South Brazil, Araucária forest, and also the famous Caatinga in the northeastern Brazil. And these biomes that are characterized by its vegetation they are also home of species that are endemic many times to these environments. So we have some representatives of these environments. Some of them occur in the Araucária forest, other in the Cerrado, as the Lobo-Guará, for example, and other that occur only in one or two biomes here in Brazil. So the number of the animals that we have in Brazil is also huge. So you can see, not only in the terrestrial biomes, we have a large number of species that are endemic to Brazil, but also in the continental basin on the Brazil coast, and of course in its rivers and lakes. Just to a glimpse of the idea of the diversity of the Brazil, the flora of the Brazil included the fungi, and fungi is not a plant, but okay. The diversity of the flora of Brazil is the highest of the world. If we could talk only about the flowering plants, the angiosperms will have more than 30,000 species of flowering plants, and this represents a number that confers to our country the title of the most diverse country in the world in terms of the flora of angiosperms. The fauna of Brazil is also very diverse, with more than 100,000 species, with about 9,000 with vertebrate species, and over 100,000 species of invertebrates. Some groups are very diverse compared to other countries. For example, the example of the birds, because Brazil is the second most diverse country in the world in number of birds, with almost 2,000 species of birds. We are losing this title to Colombia for a very few species, with almost 2,000 of birds, species of birds also. Well, the South America, in special, was a place of the world that has been explored by scientists and other people from Europe along the last 200 years. For example, Alexander von Humboldt, that was a German explorer and one of the great biogeographers of the South America. Our very famous Charles Darwin, that also explored South America in the voyager of the Beagle, also in the 19th century. His story is well reported. But many European explorers in South America went to Brazil and other countries of this region to collect plants, to collect animals, and send these plants and animals to their museum and their institutions in Europe. I just want to stress Alfred Russel Wallace and Henry Bates, that they are very famous because Russel Wallace, because he one of the co-authors of the idea of evolution by natural selection, together with Charles Darwin. Her friend and partner Henry Bates, that studied mimetism, for example, with in butterflies, and other explorers like John von Spix and his partner Marcius, that went to Brazil to collect plants and animals and musics in the mission of Austrian Brazilian mission in Brazil, but also Richard Spruce, Jonathan Poe, August de Saint-Hilaire, that walked here in Brazil collecting plants and studying our biodiversity, plants and animals. Meanwhile, in Brazil, what's going on? King Dom João XVI, he founded the National Museum in Rio de Janeiro, that was founded in 1818. Italy, it burned, has burned a few years ago. But before the foundation of the, some Brazilians also act as researchers. For example, Friar José Mariano Veloso, that published the Flora Fluminensis, but the specimens that he collected were sent to Europe, to Museu Real de Portugal and Jardim Botânico. And João Barbosa Rodrigues, that also here in Brazil, he was a Brazilian researcher and published a lot of works in the palm family, Certum palmarum brasiliensis, and genera of orchideas as well. And a little bit later, Fritz Miller, that was a German-Brazilian researcher. He was settled in the south of Brazil, and he studies mechanisms of evolution, and he studied a lot butterflies and the type of camouflage or mimicry that is called today Millerian mimicry in neotropical heliconius. So we have some researchers in Brazil, scientists in Brazil, that are present in our country in the 19th century. But the problem is with other researchers in Brazil, for example, Alípio Ribeiro, that was a Brazilian herpetologist and ichthyologist, and Frederico Carlos Reni, that was a botanist that worked in the Jardim Botânico de São Paulo. The problem with these researchers and the problem with our country is that they have no students. We didn't have in our country a system of schools and a system of faculties to guarantee the continuity of the studies of these researchers. So it's a problem of our country, and the problem with research is a problem of long time ago. One of the kind of exception is Professor Graziela Maciel Barroso, that's here, this friendly lady. He's considered the Brazilian botany first lady, and she was able to not only to study the plants that she liked, but also to train people to also research in studies of plants. So Graziella, Dr. Graziella Maciel Barroso was important because she actually founded a school of research in botany here in Brazil. So she's very special because this fact. Just to have an idea of the things, the first course in Brazil aiming at training professionals in the field of biology, 1934, in the Faculty of Philosophy of the University of São Paulo. That is the course of natural history, and in the Federal University of the Rio de Janeiro. Only in 1951, the Conselho Nacional de Pesquisa, CNPq, and CAPES were founded. And many years later, CAPES finally considered area to be called the biodiversity area in their scope, of the agents. So you can see the amount of time that was spent to consider the biodiversity area in the research in our country. Now we have, there are postgraduate programs in biodiversity in Brazil, 141 programs, and 6 of these programs are located at the University of São Paulo. Our program, the Comparative Biology program, the Entomology program, that was a sister program here in our department, the Botany program, Ecology and Zoology, and the Instituto of Biosciences at São Paulo, from the University of São Paulo, Brazil also, and the program of Animal Systematics and Museum of Zoology. So we have just in the University of São Paulo 6 programs that are considered as part of the biodiversity area in CAPES system. Different from these programs, here in our program of comparative biology, we have a focus. That is the same in the other programs. We have a focus in evolution, in the concepts of evolution. But different from these programs that we have a kind of triangle that is our shape, our basic shape in our program. This triangle is the sides of this program, and the corners of the triangle is formed by the 3 main research lines of our program: the evolutionary biology, the ecology and conservation of the biodiversity, and one of the corners of this triangle is what gives us the unique characteristics of our program, that is the corner of the history, philosophy, and teaching of biology. In entire Brazil, we have, there is another program that is called Biologia Comparada, or Comparative Biology, that is situated in the University of Maringá in the Paraná state here in Brazil, but they don't have this line of research in that program. In fact, there are no programs in the entire Brazil that shows this conformation in a triangle with this research line in the program. So this is very unique to all the programs in biodiversity in our country. And the activities that we performed here in our program, they encompass many different activities. Field work, for example, is present in many of the laboratories that are situated in our department. So you can see that the field work is important in many types of environments. Some of them are cold, some of them are hot. You can see Professor John McNamara here with his hat. And one of the laboratories of our program is the studies of this laboratory is focused in the study of the caves, biological the biodiversity in caves, that is led by Professor Maria Elina Bichuetti from the University of São Carlos, in São Carlos. So in our program, we have professors that are from our department, but also other professors and advisors that are located in other institutions. For example, Professor Maria Lina Bichuetti, Professor Leonardo Borges Maurici, Professor Facundo, all from University of São Carlos, and also professors from Sebimar and other institutions. UNESCO from Jabuticabal, Eduardo Gasparino, and other advisors. And many times, the students in this field work, they can be trained in collecting plants and also to perform analysis of the flora and fauna of these environments. And of course, when you are in the field, we can take pictures, we can take records and other kind of data, enrich the research that we performed here in our program. But of course, there is not only the field work that is performed by our laboratories. There's a important activity in after the field work that involves the laboratorial parts, and sometimes the laboratorial portion of the research is much more expensive and much more laborious than the field work that we perform. And one of the characteristics also of the program that we have advisors that can congregate students in symposium, in congress, in lab meetings, in other activities that are extremely important to bound the students together, both in the laboratories and also in different laboratories. What is important in our program is or are the scientific biological collections. Our advisors, they are many times keepers of the biological collections, and these collections are the base of the studies that are performed by these advisors and also their students. With this, we can perform taxonomics, thematics, and phylogenetic studies in a wide array of organisms. And about the corner with teaching and philosophy and science, biodiversity, this line of research is very important because we do a kind of research that is the first two fields, ecology, conservation, and also the evolutionary studies. In these research lines, we have a different profile because the work of this kind of line of research, teaching of biology, for example, is to think about the best ways to pass the information to students and other members of the society, academic one of the society, but to a public in the general. So this kind of research is extremely important to dissemination of the concepts in science and also with new ideas in evolution, new ideas in teaching and other aspects of the education in our country that is extremely necessary to a scientific education. One of the things that is performed by our students of the program and the students of the entomology postgraduate course is the Darwin Day, that is an activity. Unfortunately, last year it didn't held, but this kind of activity extremely important to bring the students of other levels of education to inside the university and to show to the students what kind of research we are doing here, and think about the best way to pass the information to the students depending on the age of the student. So Darwin Day is extremely important to these activities. We can see here some students of the postgraduate program, both in entomology and also in comparative biology. So one of the main objectives of our postgraduate program is to train group leaders in the research and other activities. We have surveyed of the places that our graduates are working now, and we know that in 70 cities in Brazil, there are former students that are lecturing, researching, keeping biological collections, or acting in governmental agencies. And some of them are also acting abroad in Chile and Europe, in Australia, and other countries. So the main objective of our program is to train group leaders, not only researchers, but people that are able to lead groups, not only to follow, but lead. Just some examples of these students. For example, Professor Mariela Castro from the University of Goiânia, that was in the part our student, postgraduate student, and after she performed her PhD abroad in Argentina, but now she is one of our advisors, and now she is in the University of Goiânia as a teacher. She studies paleontology. Other example, doctor, please, sorry about doctor, Dr. Samuel Coelho de Faria, that is also one of our graduates, and now is a researcher in the Centro de Biologia Marinha, the CBMAR in USP as well, advised by Professor John McNamara. And these researchers that act in these groups of research and lead these groups of research is a part of that our graduates are. But we have also amount of people that are working in governmental agencies, like, for example, IBAMA, Instituto Chico Mendes, and they are acting as in a job that is to watch the biodiversity, and sometimes some of them can act as well to modify or propose laws to conserve the Brazilian biodiversity better. Not because the biodiversity is beautiful to our biologists, but because biodiversity is strategic of our country. We know that our biodiversity has a value, not only because it's beautiful, it's because we like that, but because it's economically important as well. And the biologists, the graduates that we have formed in our program can also act in the conservation and the studies and impact of some disasters and other catastrophes that can occur. For example, here, the dam rupture in Mariana a few years ago, and a large amount of biologists, not only formed by our program, but other graduates of other programs, could act as agents trying to understand what was happened, trying to understand how to recompose the flora and the fauna of these regions. I've told you about the people that work in the governmental agencies, and now we have some of the most challenging our country, with many groups forcing every time to the forest code, the new forestal code here in Brazil, be revised, and the portions of forest and other areas be less protected. So our also can act to propose new laws trying to protect the flora and fauna that we have in our country. The CGEN, for example, the Genetic Heritage Management System, Sistema de Gestão do Patrimônio Genético, is also thought by biologists, and some of our graduates also act to maintain this system in proposing changes in this system to encourage the protection of our flora and of fauna. CGEN is only a set of new norms that can make biodiversity studies feasible in some degrees, because some rules that are maintained in the CGEN make the research almost impossible to our country. Well, that is only a little glimpse of what we do in our program. Thank you for your patience. It was very fast, because you know the most of the information that we have. I don't know if there are questions in the chat.
Hi, Professor. Thanks so much for your talk. It was really interesting. We don't have any question in the chat, but I have one question. Indeed, I have two, but I will focus on the first one. I believe this is a trick or a philosophical question, but we were told in the beginning of our presentation that when you have the first research collecting samples here, they usually always send the samples to out country, to Museum of Country. And until now, you usually prefer to discuss about the or the history, the Museum of History, the Natural History in USA, and you forgot our museums in Brazil, such as the Zoological Museum in São Paulo, and also Museum of Natural History in Rio de Janeiro, that we have the problem last years. What do you think about that? Do you think this is a culture thought about us, or is just no financial support for this museum? What do you think about that?
Yes, I think in the past it was a problem because we didn't have research institutions here in Brazil. For example, in the 19th century, there's no institutions, only the National Museum in Rio de Janeiro. So there are some instruments that the collection made here in Brazil, the plants, the animals, will be sent to Europe to be studied. But now I cannot agree with that, because I think we have to maintain our collections here, because we have we have the money, not so much, but we have possibilities to maintain the collections here in Brazil. You keep sending these collections to abroad, to the United States, to Japan, to United States, or other country. It's a loss of genetic diversity. So the important is to grant funds to these agencies, to museums, to other institutions, to keep the materials that are collected here in Brazil. For example, send some, we call in botany duplicates. We can send some of the duplicates abroad, for for example. The main material is kept here in Brazil, and a portion of the material can be sent to a colleague in Europe or the United States, but I think it's important to maintain these collections here in Brazil with low funding. Because if we have now low funding and we keep sending the materials to out, in the future we will have no funding and no materials. So I prefer to keep them now in what we have in Brazil. I don't know if this is the question you made.
Yeah, yes. Thank you so much. I also agree with your talk. Yeah, I believe that we have money, but I don't know if the governmental politician and also the governmental culture thinks that we need to conserve these things. Yeah. So thank you so much. Sorry to take your time.
No, it's a pleasure always, Danilo. Okay, no more questions. Okay, guys and girls, thank you so much for your time. I've seen that Professor Charbel is in the room.
Yeah, I'm here, Milton.
Yeah. Thank you, Charbel. We are a little bit late in our
No problem, no problem. I was also late because the owner of my computer, Bill Gates, planned update for now, but
okay. Thank you very much, Professor Charbel.
no problem.
I would like to introduce you before your talk. Professor Charbel is a professor at the Institute of Biology in the Federal University of Bahia, where he coordinates the Laboratory of Teaching Philosophy and History of Biology. He's a Bachelor of Biological Science from the University of Bahia, Federal University of Bahia, in Master in Education in the same university, and Doctor in Education in the University of São Paulo. And he did his postdoctoral studies at the Center for Philosophy and Nature of Science Studies in the University of Copenhagen, Denmark. Correct me if I was wrong, Charbel, please.
No, it is exactly that.
Yeah, and he coordinates the group of interdisciplinary and transdisciplinary studies in ecology and evolution that is funded by CNPq, CAPES, and FAPED, which brings together 240 researchers from 31 Brazilian institutions and 31 foreign institutions. So Professor Charbel works with many things in philosophy of biology, theoretical biology, in history of biology, in a close connection to the studies of science and education. And Professor Charbel nominated to this event by Professor Fernanda Brando, that is one of the advisors of our program, and he is, and if he would be part of our department, he would be one of the representatives of the line of history, philosophy, and teaching of education and evolution. People that are watching the YouTube, please, you can put the comments and questions in the chat, and Ariadne and Danilo send them to us here in this room. Charbel, thank you very much for your presence. It was a pleasure to us that you could spend a little bit of your time with our symposium. Thank you very much.
Okay, thank you, Milton, for the invitation. Thanks also to Fernanda for the indication. And it was a challenging one because it was around 2 weeks ago, and I was thinking, what could I talk in a symposium on comparative biology? If I had more time, I could work out some presentation of the implication theory of organism with which I work to phylogenetic inferences and things like this. But in 2 weeks and giving a lot of classes, that was not possible. And then I will try something here, which will be to bring about an example of how teaching on history and philosophy of science can be integrated into the education of scientists. I hope it will work. It is a kind of a laboratory on the course I have just given, and let's see how it works. Do you see my presentation? Because I cannot see you anymore. It's
Yes,
okay?
it's perfect. Yes.
Okay. So, unfortunately, other than the title, my other slides are in Portuguese. I couldn't translate them, but I will speak in English, and it will be the slides will be in Portuguese. So that's the title for our experience today, Philosophy of Science and Education of Scientists, an example referring to reductionism and realism. I'm not sure I'll get into reductionism depending on time. I'll ask Milton to tell me when I have 30 minutes speaking, and then I'll try to speak at most more 10 minutes so that we have time for discussion. That's okay? Is that okay?
Okay. Okay.
Okay. So I will not give an argument for why scientists, natural scientists, should have a philosophical, ethical, and political education to be really good scientists. I'll leave it this for the discussion. If someone is interested in tackling this issue, I can provide some reasons for that. So, but I'll take here this statement as a starting point. And then I will show an example from one of the graduate studies programs in which I work with the program in ecology, theory, application, and values from the Institute of Biology in Federal University of Bahia, which is a program in which the students aspire to be ecological researchers. They have a strong education methods in epistemology, in sociology of science, in philosophy of science, and in ethical theory. So that's a program that takes to the heart the idea that good scientists should have a good philosophical, ethical, and political education. And when the students are entering this program, they get a discipline with an introduction to the whole idea of the program, which is called Introduction to Ecological Theory, Application, and Values, which I just taught in March remotely because I'm now in Coimbra in Portugal as a visiting researcher. But we taught in March, whole March, with Pavel Dodonov and Claudio Reis, two other professors in the program, this course to the master's and doctoral students there. I'll give you a view on the program of the course, and then I'll try to enact here part of one of the classes, because the class on realism and reductionism takes, in fact, 4 hours, and I have only 40 minutes. So I'll give some snapshots on that. But we tackle issues like the relationships and difference between understanding and predicting. That's the opening philosophical topic of the course. Then we tackle evidence and rationality, science and values, realism and reductionism, models, levels of organization in biological systems, temporal and spatial scales, a brief history of ecology, the distancing between science and practice and decision-making. Then we have 2 classes on different fields of bioecology and the basic concepts and models in these fields. We have then some class on how to get science closer to practice, the usefulness or usability and limits of scientific models in practice and decision-making, a discussion whether ecology is a science, is a mission, or is both, a discussion of theoretical, ethical theories and scientific practice, and a short discussion on environmental education. So that's basically the coverage of the course. We try to reach a balance between presenting to the students basic ecological ideas, presenting basic philosophical ideas, and a normative, ethical, and political discussion on the relationship between doing science and acting in society, or providing grounds for people acting in society. And even though the course has 3 professors, we are all at the same time giving classes. So if one of us is the chief responsible for the class, the others are there interacting, questioning And so it was a very rich experience, in fact, this semester. And I'll give, as I said, a brief snapshot enactment of a part of a class on realism and reductionism. Because I thought, well, I have several times talked about how we can engage with philosophical and ethical and sociological issues in the education of scientists, but I didn't try to give a flavor of how it goes. So I'll try to give a flavor now. Let's see if this works. So when I discuss with the students the issue of realism, I begin usually with this example of think of someone looking at a tree, observing a tree. Then this could be something like this. So someone is observing a tree at the same level in which our experience and our perception takes place. What's usually called the mesoscale, the scale at which we live. And then we have research questions on the trees, like, for instance, the geometrical patterns of the foliage that can be answered at this time scale, at the spatial scale. But we can look closer with, for instance, a lens and start looking at geometry of pieces of the bark of the tree. And we can look even at a smaller spatial scale and look at the tissular organization, let's say, of the conducting tissues of the tree. And we can go even deeper in the spatial scale and use electron microscopy to look at cell wall structure in the bark of the tree. But we can also do something which is more in between observing and theorizing. And we can look at a tree and we can see functional parts of the tree. We are seeing exactly the same things at the same spatial scale that the first picture shows, but we are framing, interpreting differently because we're not looking in geometry and structure, we're looking at function. And we can even look at function, trying to unveil mathematical relationships between the functional traits. So there are several different ways in which we can look at a tree. And what does this mean from a perspective of our scientific practice? So that's a picture from a paper I published with my ex-student, now colleague, Nunes Neto, in 2009, I think, 2012, in fact. And that's a metaphor to what's going on here, which is very used in hierarchy theory. So every time I look at a different spatial scale at a tree, it's like I'm casting a net there. As a fisher, cast a net to get fish. And some fish get caught in the net. Some never got caught in the net because they are simply too big. They bounce back from the net. And some are never caught because they are too small. They pass through the net. And the fishermen, I work with fishermen knowledge. The fishers knows exactly which kind of net he will put in the ocean to get what kind of fish. So we could say that the fisherman has a capture window. We as science, we also have a capture window. We have an observation window that we cast on nature. And this allows us to get some information with the image we get of the world, but we also lose a lot of information, which becomes background. Information that are at a higher scale, either temporal or spatial, from our observation window, they become background. They are not captured. And also information that is smaller than our observation window. And usually, when we do a good research question, the good research question already entail a given spatial and temporal scale in which the question will be answered, and then entail a window of observation that will cast into the world. So, okay, what these basic facts on how we make questions in science and we try to answer questions in science means for a debate on realism? Why would this be important? For a debate on whether we know what's real or not, or to put in a little more technical terms, what's the relationship between our knowledge and the reality in which we live? What this entails is that nobody ever reads data in nature. When someone thinks collecting data is just about measuring something or getting some observation out of the world. And that's like some people think of obtaining data more or less as when a priest says that God speaks in his ears. Sometimes natural scientists are so naive about that. They think that they hear nature and they get in contact with nature as it is when they get data, as if data was pure, is pure information from the world. But if we think that the data we get depends on the kind of net we cast onto the world, the kind of observation window we use, then this means that the data we get is fundamentally dependent on the methodological decisions we do, which are fundamentally dependent on the kind of research question we ask. So these data are not simply read from nature. They are standardized and inscribed according to theories. Because these theories that we have about the world, which are the theories we learn when we are culturally educated as a scientist of a given field, these theories we learn, they frame the kind of questions we ask and the kind of methods we use, the kind of decisions we do about our methods, and the kind of observation window we cast into the world, and then the kind of data we get and the kind of data we forget about because they become just background for us. So this has a deep relation to the discussion on whether our knowledge has to do with reality or not, but I'll get there soon. First, let me give you an example from which we studied in this paper that appeared in History and Philosophy of Life Sciences 3 years ago, in which we were trying to investigate how an experimental research tradition was built in ecology from studies on rock seashores by people like Joseph Connell or Robert Payne. And we discussed, well, these are the first generation of ecologists that really framed experiments that could be done with reasonable control of conditions or accommodation of conditions in nature. And they domesticated nature to get some kind of data. They standardized it, they inscribed nature into a framework. We could allow them to obtain patterns in their experiments despite the complexity and the variability of the environments in which they were working. So here we have Joseph Connell with his observation window. His experiment was framing these 1 meter per 1 meter square boxes where they do exclusion experiments. You take out, let's say, a competitor or take out a predator and see what happens to the colonization of new organisms in this small square. So this is the observation window from him. He's not simply studying the rock seashore as it is. He's looking at the rock seashore from a very specific angle, decided upon trying to, decided methodologically making decisions to try to answer very specific questions on the role of interspecific competition and predation, the structuring of ecological communities. And they got fantastic results that were very decisive for interspecific competition to be regarded as a very important factor in structuring ecological communities in a time in science where the idea that ecological communities are structured by abiotic factors was completely dominant in the scientific community. And they turned this table upside down and they brought biotic factors as important factors for understanding how ecological communities are structured. And then they tried to repeat these experiments. So Paul Dayton, the third researcher here, it was a student of Robert Payne. And Robert Payne did these studies in the west coast of the United States. And Paul Dayton tried to repeat the same experiment in the east coast of the United States. But unfortunately, the same patterns that Robert Payne had seen 15 years before were not obtained by Paul Dayton in the east coast of the United States in the 70s. On the other hand, on the contrary, in fact, there were a lot of stochasticity. The patterns were completely disrupted by stochastic effects, which Penn told to Dayton, look, this is noise. You need to plan your experiments in a way that to get rid of this noise. And there was a clash between Dayton and Payne because Dayton said, no, I don't think it is noise. I think these stochastic factors, they play a key role in explaining how the communities are structured. Because he was thinking, look, why there is stochasticity in the east coast of the United States? Because of storms, because of hurricanes. There are many, many, many hurricanes and storms in these coasts. And sometimes logs enter the rock seashore and completely destroy communities, completely change the structure of the communities. And if we don't put these stochastic factors into the picture, we cannot really understand how the rock seashore communities in the east of the United States can be understood. We can be structured. We need to understand that. And that was the beginning of an important story in ecology when stochastic factors became also an explanatory factor for the structure of ecological communities, besides biotic and abiotic factors. So noise was not noise. Noise was explanatory, was a causal factor in the process. So this is a beautiful story about how these people are not listening to nature when getting data. They are structuring the experiments in a way that domesticate nature and get homogeneous results, but sometimes it's not possible to do so, and we then need to bring stochasticity as an explanatory factor into the picture. So what about this story about observation windows mean? Means that there are not pure data out there that should be interpreted. There are not two moments. One moment we check data from the nature, and then another moment when I interpret the data, such that the human factor, the human interpretative factor would only become important when we are analyzing data. No, gathering data is already an act of interpretation. Every perception is an act of interpretation. And this is not great news in philosophy of science, because since the end of the 19th century, when Gestalt psychologists started working with perception and interpretation, they showed to us that there's no way you can see anything. You can only see that something is something. Seeing is a propositional attitude. Seeing has always a content. You see what you can see. You see what you are prepared to see. So the Gestalt psychologists did a lot of experiments with these ambiguous pictures, like this one. Is this a duck or is this a rabbit? Well, this is both a duck and a rabbit. But what this picture says to us is very profound. It says the following. Well, when I look at these pixels here with the lights of the computer, I get information from nature based on photons. These photons reach my retina, and there is only one information coming from nature in each photon. There are not two informations, only one information. So if it is only one information, I'll have a pattern of photonic excitation in my retina that has only one information. So how can I see a duck and a rabbit? How can I do that? How can I see double if there is only one information coming from nature? So what means is that our brain is playing an active part, and our brain can do two interpretations of a single piece of information coming from photons. And as our brain do two interpretations, we have a double perception. But this means also that we cannot see this only. We either see a duck or see a rabbit, depending on how my brain actively interprets the information that comes from nature. My brain is participating in the process. That's another way of coming to the conclusion that nobody perceives and then later interprets. Everybody perceives and interprets at the same time. Today, we have the physiological basis to understand why this happens, because the information that gets into my retina and travels to the brain in the optical nerve, it will be fragmented when it enters the visual area in my brain. The visual area is very specialized. There are neural maps for texture, neural maps for color, neural maps for verticals, neural maps for horizontals, neural maps for edges. And when I see something fantastic happens, because the information that I got from nature through my eyes is completely fragmented, and then my brain puts everything back together. How it does this? Because of something called reentry circuits, in which one neural map signals to the other neural maps, and the other neural maps signal back as the output of the neural maps, such that we see not a fragmented thing, we see something. But then there is a role of the brain in binding the information that was fragmented. And we know now from experimental evidence that even when there is some information lacking, let's say I look at a share, look very fast, I simply move my face. To remember what I saw, I see a share. I will see a share, even if there is no photon coming from some parts of the share to my retina, because the brain infers that that's a share. And then when the neural maps in the visual area firing to each other to synchronize the outputs, some neural maps that didn't receive any external output from the sense organs, they get into the play because they receive the firings, and then they receive the reentry circuits, and then they fire out the output. They fire the output without any inputs, meaning that parts of the seed of the share I see from nature there. There is only inference by the brain. And now there are even experiments when you can fool things depending on how you manipulate a kind of interpretation that is always together with perception. So why is this important? Because if we don't read data out of nature, realist about knowledge. What means to be a realist about knowledge? Is to assume that there is a meaningful relationship between the knowledge we build and the reality in which we live in. It means that our knowledge is not a complete construction, but there is something out there from which we get information. And there is a way in which what we know about what's out there has some meaningful relation to what's out there. Okay, but can you be a realist naively? No, if you think about how we get data from the world and how we observe the world, or even how we perceive the world, we cannot be naive realists anymore. If there is a relation between knowledge and reality, it's not a mirroring relation. There is no mirror in our mind that simply reflects what's in nature. If there is a relation to be proposed between reality and knowledge, we should do our work better. We should do more than simply naively accept that we somehow have privileged access to the world out there, either because of God or because of method. We don't have any privileged access. So if we have some access to reality, we need to work more to understand what kind of relation is this. So that's the starting point to discuss realism. The starting point is something that Wittgenstein, the Austrian philosopher, called philosophical therapy. Before you think philosophically, in a philosophically sophisticated way about some issues, you should first say goodbye to some wrong intuitions we have. So naive realism is a wrong intuition. Unfortunately, it's a wrong intuition that has been taught to people since basic education. And some people finish their doctoral studies and still they didn't get rid of this wrong intuition. But the first step to really discuss realism in a proper and sophisticated way is to get rid of this wrong intuition. So the first part of everything I said here is just philosophical therapy. Now we can get into, supposing that I'm convincing you to get rid of naive realism, we can really begin to think about the debate about realism in philosophy of science. And the first problem is that there is not one single debate about realism in philosophy of science, but there are three debates. Two of them are not so important when it comes to discuss natural sciences. One of them is really important, but it's important to see the three of them such that we don't get confused, because it is a big confusion when you are discussing one question and we start discussing another question in the middle of the discussion. So it's important to say something about these three forms of realism, to leave two of them out of the picture and only one of them into our picture. The first one is a debate that comes from the ancient Greece, ancient times, and was very important up to the Middle Ages and became not so important after that. It's a debate on whether the universals are real. All our concepts about the world are universal concepts. Are these universal concepts real in some sense? Aristotle, for instance, say, yeah, they are real. They are real because they are shared properties between particulars. Plato would say, no, they are real because there's a world of ideas, like in the cave myth that Plato explains. So there is a world of ideas where the concepts live there, they are there, and we reflect this world of ideas. Aristotle said, no, there is no world of ideas. Our ideas, our universal ideas are just shared commonalities between particular that we think about it. And the nominalists, they would say, oh, no, they are only particulars. The real, the concepts, they are not real. They are just in our minds. So this is the discussion. Jorge Luis Borges, in his fantastic book, Ficciones, tells the story of Funes. Funes was a nominalist. So he was very worried about the fact that someone called dog, the same dog that one sees at 3 and 15 from the side, and they say dog again. When they look at the god and the dog, they see at 3:45 seen from the front. So you cannot call them dog because they are different particulars. So only particulars exist. Well, this is an interesting discussion, but it's not so interesting in philosophy of science. Basically, all philosophers of science are realist about universals. Another debate that people often think about it, but it's not so important in discuss natural science, is the debate about the daily objects. And you have the famous debate between realists like John Locke, a British philosopher, and another British philosopher, George Berkeley, which was an idealist and solipsist thinker. And George Berkeley would say, well, everything we see is a creation of our minds. There is nothing really there. And John Locke would say, no. There is something out there. It's not everything a creation of our mind. Well, very interesting philosophical discussion, but when we discuss realism in philosophy of science, we are not talking about this. Everybody who is discussing realism in philosophy of science are realists about daily objects and about our natural experience. The debate on philosophy of science, which I'll call here the debate on scientific realism, is a debate about the reality of non-observable theoretical concepts. So when we do science, we do observation, but we also think about concepts that are not observed, like natural selection, gene. I don't observe genes. I observe bands in a gel, in a molecular biology lab. And from this observation, I make inferences about genes. I don't observe natural selection. I observe consequences of natural selection, and I make inferences about natural selection. And an inference is evidently not an observation. An inference is an act of our minds. It is a problem that when we teach natural science for people, we often call inferences observations and make people completely confused about this. But what we observe, for instance, let's say I take an equipment and I measure the pH of a sample of water. And I say, well, it is a neutral because the pH is 7. If I say I observed that the pH of this sample of water is 7, I'm completely wrong. What I observed was that there was a needle in the equipment, the needle points to 7. That's what I observed. Because when I start talking about pH is a universal concept. I'm making an inference, a very good inference, very well supported. But it is an inference to say, well, the pH is 7, then the solution is neutral. So we need to be more careful when we educate people in science to make a good separation between inference and observation. And that's important because The whole discussion on realism in science is about these things, these concepts that we infer, we are not observing. Let's say I'm testing a model coming from a theory. This model has a theoretical component, which made of universal concepts that are not observable. And there is an empirical component, which made of observable events in nature, which, if my model is good, is closely related to the theoretical component. There is a good logic in the model when the theoretical component and the empirical component are properly related. If the empirical component is not properly related to the theoretical component, that's a mess. Because when I test a model, I don't know what I'm testing because I don't have a connection between empirical events and the theory. What we test and experience are predictions that come from the empirical components of the model. And then I do go there and I make a prediction, I test a prediction. Let's say that experience shows data that agrees with the prediction of the model. At this point, there is no discussion about philosophy of science about the truth of the prediction. If I made a prediction in a specific experimental design, and the prediction was verified in that experimental design, within the experience that is framed by that experimental design, I can even use truth by correspondence. It's simply true that I predict X and I saw X. Is simply true that the prediction because I saw X. There's no problem with this. There is a concept in philosophy of science to say this. It's called empirical adequacy. So when I test a prediction from a model and the experience agrees with the prediction, we can say the prediction is empirically adequate. And there will be no discussion about philosophers of science about this. That's accepted. The problem comes here. Once we have the empirical adequacy of the model, the prediction of the models agrees with the results of the experience inside an experimental design, what can we infer about the theoretical component which is not observable? That's where the realists and the anti-realists in science, in philosophy of science, will fight each other. The realists will say, well, if my model is empirically adequate, I can take this empirical adequacy and make inferences about the truth, even if only approximate, of the theoretical non-observable components. So the realists, they fly from experience into an acceptance of the truth of something that was not observed because they are maintaining a connection between what I empirically see and what I theoretically think in terms of truth. The anti-realists will say, no, you cannot do this inference. Or some, like myself, will try to remain agnostic about it. We say, well, I don't know if it is true, I don't know if it is false, I'm not interested in this, because this is an unanswerable question. I will never know if the theoretical non-observation components are true or not. So I'll prefer not to say anything about it. I think agnostics like myself should be better called non-realists, the anti-realists, because they are not saying it is not true, it is not real. They're simply saying, I'll make no judgments about it. But why would someone on earth think about this? Well, the issue is, our experience with the world is the only thing we have. Everything we think we do takes place in our experience. As we are self-conscious beings, we are stuck within our experience. We can never go beyond our experience because the simple fact that we are we means that we cannot go beyond our experience. We are simply stuck here. Experience gives us everything and takes everything out of us. We will never know how is the world out of experience because we are simply imprisoned into experience, because that's what it is to be ourselves. So a non-realist will say, or an anti-realist will say, well, if I'm stuck into experience, what's the most parsimonious decision? Well, the most parsimonial decision is to make no inference beyond experience. And if I make inferences about the truth of my theoretical ideas from experience, I will, by definition, go beyond experience. So we could say that the realists in philosophy of science and also in science, they are happy enough to go beyond experience, to accept the truth of theoretical concepts. And the anti-realists and non-realists, they are not so happy about it. They try to be metaphysically more parsimonial, and they don't go beyond experience. It's interesting that when we discuss the theoretical non-observable components of our theories, that is when we discuss genes or natural selection, we are doing metaphysics, because we are doing something that goes beyond experience. Now, then, this is not always recognized in natural sciences. But then comes the question, okay, then you say nothing about the theoretical components of theories, you say, well, I will stay in experience. Then I could say, well, then give up doing theory. Well, I'll never give up doing theory, because if you don't do theory, you don't explain the world, you don't predict anything, you don't understand anything without theories. Data is not enough. So there should be some way of going beyond experience, but how? So the question I'll ask is this: how can we judge the theoretical component, which is non-observable, of our models and theory from a non-realistic perspective? Well, we can do pragmatic judgments about the heuristic power of the theoretical components of models and theories. What do I mean by this? Well, I can choose a theory A instead of theory B, not saying that, well, because there are more experiments supporting the theoretical ideas of theory A should be better than theory B. Because look, I really don't know. I really don't know about what will happen in the future. It may be that from the time I say theory A is better than B, because of the empirical adequacy of its models, I can be turning the corner to 50 years of research showing that theory B is better from the point of view of empirical adequacy. So what a non-realist would say, well, I will choose theory A not because it's more empirically adequate. I will choose theory A because it's more powerful for us to build hypotheses, to build models, because we learn more when we use theory A. That's what I mean by pragmatic judgments. I judge the theories and models based on how well they perform as tools for learning and investigating the world. Well, what I said up to now might suggest to you that there are only two poles in this discussion. Either you are a realist or anti-realist. Well, unfortunately, the things are much more complicated, and this picture shows how many forms of realism and anti-realism there are. There are several different forms. I'll not explain each of them now. And there are several different authors and philosophers that will be located along this spectrum, this range, from realism to anti-realism. And I'm somewhere here. Not so anti-realist, but somewhat, with the position I would call non-realism. And this I'm together here with the kind of philosophical school that I follow. I'm a pragmatist, and with the authors that most influenced my thinking: Peirce, Dewey, and von Frassen. So that, and Putnam. So I'm here in between this place. What I tell the students, well, now you have to find out where you are in this picture, and not simply think that I'm right and then follow my words, because look, it's very complicated. I'm just presenting one perspective on this. And to finish, and as I expect I will not get into reductionism, but I'll try to finish the scientific realism part. So what I'd like to say more. First, this discussion about realism is a very important discussion, because there is a divergence between people who are realist or not realist about the nature of science and the goal of science. So they do science differently. You do science differently depending on how you locate yourself here. So that's why it is important. That's an argument for why a philosophical education is important for natural science. Otherwise, you do science with a unchecked luggage of philosophy, with a lot of intuitions that you never thought about it. So it's better to think about it. So for realists, the goal of science is to discover truths about the world from theories, because they understand theoretical concepts as true, at least approximately true, and the entities that these concepts postulate to exist in the real world, they are assumed to be real. And an anti-realist will say, well, the goal of science is not to discover truths about the world. In fact, truth is a very limited concept to think about knowledge. Let's not think about truth. Let's think about acting, about activities. So anti-realists will say, well, the goal of science is to provide us empirically adequate tools that are good enough to deal with the world. And for an anti-realist, the theoretical concepts are understood as useful fictions. Let's see what a useful fiction means. But the question someone would try to answer from this perspective is, do you search true theories? Then you are a realist. Do you search only empirically adequate theories that are good tools? Then you are probably an anti-realist. But what does it mean to say that a theoretical concept is a useful fiction? There is this bright book by the Brazilian philosopher of science, Luiz Henrique de Araújo Dutra, in which he tries to explain this with a marvelous analogy. And the analogy is with literature. Think of a piece of literature. Let's say you are reading Dom Casmurro from Machado de Assis. Well, Capitu, main character in Dom Casmurro, may be real. Perhaps Machado de Assis knew something in his experience, someone in his experience, that was just like Capitu, that gave him the inspiration to write about Capitu or about Dom Casmurro. Well, but even then, the character he created, Machado de Assis created, are fictions, because they are not the real things. They may exist in reality, but they are fictions. And there is no point in asking about the quality of Dom Casmurro depending on the judgments on whether Capitu existed or not. This is a no questions, completely unimportant. The book will be really good even if Capitu never existed. And the book will be really useful even if Capitu never existed. The existence of Capitu is meaningless in relation to the quality and utility of the literary work. So we can be agnostic about the existence of Capitu and say Dom Casmurro is a hell of a book. Well, we can say exactly the same about scientific theories. There is no point in asking about the quality of a theory depending on whether genes exist or natural selection exists. This is simply the wrong questions for a non-realist. They are wrong first because they are not answerable. You will never know if genes exist or if natural selections exist. This doesn't mean that they don't exist. It just means that we are making a wrong question. The good question is about what work these theoretical concepts do. They do good work. They do useful work. If they do good and useful work, it doesn't matter if they exist or not. They are good concepts. And the theory that is built around these concepts are equally good theories. So we can be agnostic about the existence of theoretical concepts, and this doesn't matter for judging the quality of the theory. Because as I said, when we judge the quality of the theory, the quality of the concepts that are part of the theory, we can simply forget about existence and make more important questions, which are the consequences. What are the consequences of thinking that natural selection exists? What are the consequences of thinking that genes exist? Pragmatically, what does this mean? Are we capable of doing good testable predictions, build incredibly nice new models, make fantastic new questions? Oh, the consequences are great. Keep natural selection, keep gene, and forget about asking about existence. That's basically applying what Charles Sanders Peirce called the pragmatic maxim. To develop its meaning of a thought, we have simply to determine what habits it produces. For what a thing means is simply what habits it involves. So if we apply this to science, we get objective pragmatism. If you want to establish the value of theoretical concepts, think about the concepts that follow from assuming, there's consequences that follow from assuming those concepts to be valid, without postulating its existence in nature, remaining agnostic about the reality of the concepts. One final word about a complication with the distinction between realism of entities and realism of theories. This comes, for instance, in first time in this book by Ian Hacking from 1983. And what's realism of theories? Is the idea that theories, when are correctly accepted, are true or close to truth. And that realism about theories is the idea that theories can be justified, adequate, acceptable, but never true, not even approximately true, because they are just useful tools. And we have realism of entities. The entities that the theory correctly accepted postulate exist independently of us. And anti-realism of entities. The entities that theory postulates are fictions, logical constructions that we use to think about the world. And an objective pragmatist, like myself, is agnostic, concerning the reality of theories and the reality of entities, but not agnostics about the consequence of assuming some theories and some entities in experience. So this amounts to an agnosticism about theories, which is the claim that theories can be justified, adequate, acceptable, they are useful tools, and the judgment about its truth should be suspended. Agnosticism about entities, the entities that the theories postulates are logical constructions used to think about the world, and the judgments about its existence should be suspended. But we can and we should do realistic judgments about the consequence of assuming theories and entities in our practices and our experiences. The consequence of thinking of theory A and not of theory B have true consequences in our practices and our experiences. And as far as we are talking about our practices and about our experience, we can be realists with no problem at all. I think that's it. We can go to discussion. It was possible to follow. It was okay?
Yes.
Okay. It's complicated to give a talk like this because you don't see the others, you don't have a clue about whether people are following you or not. It's a strange experience.
Well, my mind is blowing here. Thank you, Thiago, for your speech. I don't know if Danilo has some questions from the chat in the YouTube, or Ana Paula or Ariadne.
Hi, Professor. We didn't receive any question in the chat, but I have my own question. So first, Professor Chabel was really interesting talk. I will open my video camera. Was really interesting. Wow, so many interesting points. It's like so complicated area for me. I don't know where I am yet, so I have to get all your this video again and watch to get some of your points. But so about my question is about the beginning of your presentation when you show the picture of duck and rabbits. So in our fields, and of course in the scientific fields, when you have the duck and the rabbit, sometimes it's impossible to see the rabbit or to see the duck. Sometimes you just see one or other. And for example, if you see the duck now and I publish a paper, but in 2 or 3 years I found the rabbit, how can I act to solve this problem? The other thing is, I think it's a difficult question. Sorry.
Maturana had in his lab the 12 human rights, and he added a 13th. The 13th was the right to change your mind. So you basically have the right to change your mind. And this is something that we have a hard time to explain students and the lay public about it. I remember one time there was discovery in Asia. Stephen Hawking says Stephen Hawking was wrong. Well, who was wrong and who made the cover? Because it was something completely stupid, because Stephen Hawking had published a paper in the 90s, and in 2000, he published a paper contradicting what he said in the 90s. He saw a duck, now he's seen a rabbit. What a scientist says, well, I saw a duck, now I got, oh, it is a rabbit. That's what we do. And he's not saying he was wrong, because you can't be wrong when 10 years after you say, well, it was not like I said. That's not the same as being wrong. It's much more complex than that, because you know that in the history of science, conclusions can change, depending on new data, depending not only on new data, on new ideas. Someone brings a concept and you say, well, that data I saw, it's something, we can have the same piece of data. And depending on how you frame the question, you think conceptually, the data means something completely different. So there's, I collaborate with Ana Soto, from Argentina, who works in Tufts. She has this incredible example. She and Carlos Sonnenschein, also Argentina, work in Tufts. The example of all people thought about hormones. They did experiments on hormones, completely framed by the idea that hormones were trigger processes. And then people concluded after a lot of experiments, well, hormones trigger processes. And they made experiments showing that, for instance, for estrogen, what hormones were doing in their experiments was there was an inhibition triggered by a component of blood serum, and the hormone was not triggering the process, it was fighting the inhibition. So it's completely different interpretation. The hormone is not the process that's triggering the other process. There was something triggered before, with an inhibition. The hormone is reversing something that was triggered before. Well, the data you could have, it could be the same. You can look at the action of a hormone. If you don't frame the experiment shows this, because they frame the experiment to show this, because they had the hint that something was wrong. Then they frame the experiment to show. But if you make an experiment, you take an extract of a gland, then you put it in cell culture, and then the cells respond. Well, if you see this, you can see, well, the hormone is triggering cell response. Or you can say, well, there was something inhibiting a cell process, the hormone is counteracting the inhibition. Duck and rabbit, that's simply part of science. We can't get the whole picture. Our situation is much worse than the duck and the rabbit, because in the duck and the rabbit, there are two interpretations for one single instance. We have hundreds of interpretations, and we have interpretation we didn't think of, and we will think in the future. That's simply part of science. But only one final question, because every time we discuss this with people, I tell high school teachers, you should discuss this, but there is a problem. People are usually very naive philosophically. So sometimes when a teacher tells in a more sophisticated way how science works, you have a very deeply religious student who says, oh, no, then I don't want to know about science anymore, because I know the truth. Yeah, you don't know the truth. Nobody knows the truth. So there is some deconstruction to be made for people, because otherwise you'll be, oh, some have the truth, others don't have the truth. No, nobody has the truth. So the situation is simply more complicated than that. But some people, unfortunately, they are so naive philosophically that they cannot get it. And we have to do something about this educationally, because they are not so naive spontaneously. Something happened that made them get into that position.
Oh, that's great, Professor. I had a second question, but I believe you also respond that. And I believe you gave us two important messages. That first one, we can change our ideas, we can change our minds, and you can need to do that to become better and better every day. And the second question is that you, for example, if you have 2 points, you have to discuss about them. You have to use your best point of view to discuss one another, and you can choose one another question. So that's excellent. Thanks so much again.
Only one footnote for this, because we work in science, and science is a collective. So we change our ideas in science constrained by the collectivity to which we belong. And that's very important for new researchers to know. Because otherwise, there are some people, they become revolutionaries all the time. So they want to revolutionize everything. But science works based on established bodies of knowledge that will change only slowly. And that's important because otherwise we'll be doing science to answer the first questions all the time. We'll build a building of ideas because we take some ideas for granted. So if you are now new molecular biology and say, well, my thesis will be to say that the double helix model is wrong, bad choice of research question, because it's you against the crowd. So we need to see how we are framed by the society, the community we belong, to see where the changes are to happen and not become a revolutionary for all causes when there are no chances of change in some points, because this will harm your career very badly.
Yeah, you're right.
There is a question by Ariadne, I think.
Yeah, thank you. We have some questions in the YouTube chat. Let's see. So the first one that I found here is the Silvio. So Silvio is our doctorate student, PhD student, sorry. What's your position about the realism and anti-realism, philosophical realism and anti-realism, when you think about social science? And what is the philosophical components that could be applied for this field?
Well, my position about the social science is exactly the same. It's exactly the same. So for me, the theoretical concepts in social science have the same status as the concepts in natural science, and you need to judge them pragmatically, depending on how well they perform in our role of trying to learn and understand more about the world. So I don't have a distinction, but that's important because, for instance, usually people who are non-realists, they usually get more shared positions depending on the scientific field, because it is more generalizable than non-realist position. For realists, it's harder, because someone can be a very strong realist about biological systems and an anti-realist about social sciences. Because they'll say also, now in ecology, there are some examples. So people are very realist about organisms, but they deny the existence of ecosystems. So they are anti-realist about ecosystems. So realist people usually have this variation across science, depending on how far they bet on the inference from the empirical data to the reality of the non-observables. Non-realist people, as they don't do, they're not completely pragmatic about the non-observables, they usually get more standardized position. For any science, is simply the same. What we can say is some of the science sometimes have more powerful concepts than others, but I don't think the social science have less powerful concepts than the natural sciences.
Thank you, Professor. I believe that Ariadne wants to talk now.
Yeah. Good morning. Presentation that every researcher give to a sign in the semiotic point of view. We can say that the interpretation of the results also depends on the significant level of the researcher.
Yes and no. Yes, in the sense that without interpretation, the research cannot even get data. So if you don't do any interpretation, you don't have it, not even a research question. You build a research question. You are already choosing how you frame your observational window, which scales you work and so forth. But it's not individual by individual basis, because I could say that in the decisions of researchers, the whole community of researchers is present. Speaks, a whole community speaks. Lorraine Daston and Peter Gallison, two historians of science, call this collective empiricism. researcher, when he's educated to become a researcher in a certain field, passes through a natural development process to the process that we pass when we enter into any culture. You build, when you become a educated researcher in a certain community, you build in yourself, you internalize it, a number of values, ideas, theories, ways of thinking, even anecdotes, even a way of being in the world. So it's very powerful, the formation of scientists by communities. So even though we are interpreting our data, it is always intersubjective. Not one subject doing that, only one individual is intersubjective. And this is a very important idea. The idea. For instance, Ellen Longino, a feminist philosopher of science, will build a notion of objectivity based on this idea of intersubjectivity, saying, well, and that's really important because, look, the fact that we question ideas like objectivity, truth, putting nothing in place and sometimes open the way to what we live now, where people think everything is opinion. So if you say, well, look, global warming has an anthropic cause, someone is, no, that's your opinion, my opinion. Well, it's not opinion. There is a distinction to be made between simply having opinions and having knowledge. And the concept of objectivity, which in some fields, like science education, for instance, people hate the idea of objectivity. I don't hate the idea of objectivity. I love the idea of objectivity. But we shouldn't be naive about it. If you think knowledge is objective because sometimes mirror the word, that's simply wrong. No knowledge mirrors the word. If you think knowledge is objective because it's neutral, has no influence by values and interests, no knowledge like that. So there's an empty set. But Ellen Longino says, look, knowledge is objective when it is a product of a community.
Thank you, Professor.
Thank you, Charbel. I think there are 3 questions in the chat, but I don't know how to collect them. Danilo or Ariadne could help me.
Yeah, don't worry. Andrea already do that. So I can also read the questions. The second question, first, she would like to thank you for the excellent talking. And Professor Fernando asked, Charbel, the ambiguous image of habit duck illustrates very well how paradigms, our reality, changes in science. As scientists, we are trained to understand that are in movement. I believe that one of the explanations of scientific negationism is in the misunderstanding of science dynamism. What do you think about that? And thank you for your talk.
Science, I didn't get the last word. It's about science, dialectics, what's it?
Let's see where it is. Negationism. Negationism is true.
Negationism is about science, and then the last word. That's what I didn't get.
Dynamism. Dynamic.
Dynamism. Okay. Well, for sure. Well, it's difficult because First of all, let me answer the first part before. The first part is that about paradigms. Well, it's true that it can show something about paradigms, but there are sciences that work perfectly well without paradigms. Because a paradigm, technically speaking, as Thomas Kuhn finally defined it, because in the first version of Thomas Kuhn's book, is famous for the fact that there are 60 different concepts of paradigm along the book. So the concept was fluctuating wildly. But in the second edition, we solved this problem and said, well, a paradigm are two things. One is disciplinary metrics that guides the whole research inside a discipline, a scientific discipline, and is an exemplar in the sense that it gives the researchers clues, key clues about how to make questions, how to answer questions, how to frame methods, how to interpret the results, and so forth. And a paradigm has this property of being unitary. One field has one paradigm per time. And then you have scientific revolution, comes another paradigm. And these change of perspectives, these gestalt changes, they happen when you change from one paradigm to another paradigm. And Kuhn himself writes about it in The Structure of Revolution Theories, his most famous book. The Structure of Theoretical Revolution. The Structure of Scientific Revolution is my most famous book. And however, there are sciences in which more than one paradigm exists at the same time. No, not more than one paradigm, because I cannot call paradigm, because paradigm is unitary. More than one research program or more than one research tradition exists at the same time. And in this case, it's quite interesting, because what you get diachronically in a science that has paradigms, you only have the gestalt change when you move a long time from another paradigm. You have synchronically in a field that have different research traditions. If you look at learning from a cognitivist perspective, will look completely different from what's learning from a social interactionist perspective. And this happens at the same time in the education community, for instance. So that's one point. The other point is, well, it's not only the dynamism of science that makes people have a hard time understanding what science is about, and this really contributes to negationism. And I don't know if the word negation, this doesn't happen. Denialism in English, I think. Well, this thing, negationism. Yeah. Because look, we try to teach science to people since they are young children. And they learn science for 11 years. But how is it possible that they finish high school, they don't have a clue about how science works? Well, it is perfectly possible, because we teach the products of the science all the time, and we rarely teach the processes of science. They don't understand what is science about, because we are teaching the parts of the flower, we are teaching the classification of ecological interactions, we are teaching how many organelles there are in a cell, we are teaching how to solve classical mechanics problems, but we are not teaching, well, how can people know about this stuff? What kind of questions they make? Why these questions are answered this way? Why these answers are accepted, those answers are not accepted? What picture of the world we are building when we do science? We don't tackle these issues. And even worse than that, we put such a burden on the mind of people that they cannot really think about what science is, because they are simply getting immersed by an immense amount of content that they don't understand. There is this metaphor by John Solomon, a British science education researcher, saying that when people are around 10 years of age, 9 to 10 years of age, the train of science becomes a bullet train through the landscape of Japan. And they pass very fast through several concepts. And then in the end, you ask, well, what you learned about the Japanese culture by traveling in the bullet train through Japan several times? Probably didn't learn anything about the Japanese culture. It is the same about science. People don't learn anything because it is so fast. It is so overcrowded. Complex ideas are sometimes explained once a year. How you can get a complex idea being explained once a year? You have to explain a complex idea several times. And every time people say, well, but there's not enough time because the curricula, well, the curricula is overstuffed. What point it is, one of my students made an estimate of how many new concepts are learned by high school biology students in Brazil. This is a paper from 2011. He got the amazing picture that it is expected along 3 years of high school, a Brazilian student learned 3,300 concepts. This means they should learn 5 concepts per minute of class. Well, how can this be possible? This is evidently impossible. So there is something completely wrong. So people don't understand how dynamic science is because people don't understand basically anything about science. And we should change this. And people are saying that this should be changed for 40 years, 50 years. But the system seems incredibly resistant to change. Still, people are worried about how many concepts you cover of your book per year when you are teaching biology or any other science discipline in high school or whatever.
Thank you, Professor. We still have 2 another questions. It's okay for you answer them? Okay, that's great. So the third one is from Fernando Guedes. So he said, excellent lecture. The fact that many different models have a certain coherence between them could in principle suggest, even if I didn't foolproof, that there is really that there is a reality behind them.
Well, I think only means that they are coherent, that they form a good family of models, and possibly the theory they constitute is a good theory because the models are very coherent to one another. But I don't see how can we project our conclusion that they will be closer to reality because of that. Because we're having in the history of science examples of very coherent theories that were eventually shown to be false. For instance, classical mechanics. Classical mechanics is very coherent, it's very useful to deal with movements on Earth, but it was superseded by Einsteinian theory, from which classical mechanics is a special case and is very coherent. So I don't think we can get this from coherency. If I'm to be fair enough to the more sophisticated realists, they use arguments like, for instance, there is an argument by Richard Boyd, which is one of the more hard-nosed realists we have in the philosophy of science. You say, well, the success of science would be a cosmic coincidence if we wouldn't be getting something of reality. So that's one realist argument. I don't agree, but it is a stronger argument. It's harder to defeat. But from coherence, I think coherence shows that we are doing good theoretical work, more than we are getting into reality. But all that being said, I would say that when we get high levels of coherence, everything else being equal, we tend to have more pragmatically useful models and theories, because we have like a space to navigate. So if I want to understand, for instance, the impact of an invasive system, invasive species on an ecological system, and I have a good family of models, I can see which biological assumptions are supported by the biology of the invasive species, and I can choose which model is framed by those biological assumptions, and this will make me more capable of understanding. I wouldn't say predicting is much more complicated, but at least of understanding what the invasive species is doing. There is I got this example of invasion biology because there is a group of researchers in invasion biology thinking exactly in this manner and trying to build something they call the hierarchy of hypotheses, trying to organize the hypotheses about invasive species in a single framework, looking for coherence across the several models. And the idea is this: well, if you get a coherent set of models, then it will be much easier to apply our understanding to specific cases, because you can know, well, this case takes me to this harbor in my navigation. That's the model I get it. So this model is the most pragmatically useful to think about this case of invasive species.
Okay, that's great. So the last question is from Ana Carolina Ferreira Barbara. Professor Charbel, I think that the lack of self-consciousness of scientists in general about their own values, their place in society, and the historical background behind these values influence them misunderstand scientific data as true and perfectly reflect information about nature. Would you agree with me? I don't know if this question is too.
That's part of the issue. But I think one thing we need to ponder about is how natural scientists got to be educated like they have been educated in the last half of the 20th century, which make at least part of them to be really naive about the things you are talking, which values are framing my research. When I choose to investigate, let's say, heart diseases, and I don't choose to investigate malaria, what this has to do with the values I have, which has to do with my position in society. The fact that natural science got to be more naive about this has to do with a process that happened with science in the 20th century, which I think is important for us to understand, to see how we can do things differently. So, for instance, this program, I'm very happy to participate with the program Ecology and Wisdom Biology, has this goal of educating scientists that think differently. So, for instance, one of the things they will learn in the course is you have values. These values frame your methodological decisions. You have two choices. You can have these values and check the luggage, which means that an incredibly important factor in how you frame your question, try to answer your questions, is completely beyond your control because you don't know what they are. Or you can check the luggage. And I say to them, look, one criteria for being a good scientist is to be explicit about your values and say exactly which role your values play in your research, which side you are, what are your interests, why you are doing this or that research, why you use this or that method. So it should be explicit about your values, because when you're explicit about your values, two things happen. One, other people who don't agree with your values can read your work being critical about your values. And second, you can be more self-conscious about the choices you are making, and you can make better choices that better agrees with your values, or sometimes you can change your values because you discover that, well, that's not exactly how I would think of myself in the world. So that's our dream of educating as scientists. But it's important to ask what happened. Why? Because if you look we don't need to talk about the 19th century scientists like Darwin. We take the scientists educated in the first half of the 20th century. You take a guy like Ernst Mayr, for instance, who had philosophical education, knew a lot about philosophy and history, even though he was an expert. He was an expert in bird systematics, even though a significant part of the work he did in his life had nothing to do with bird systematics, because that's what a broad education of a scientist allows a scientist to do, to go beyond the frame of his or her own discipline. But what happened that made scientists from the second half of the 20th century very different from scientists from the first half is an incredibly important process about science that has to do with the role of science in society. So if you look at the 19th century, universities didn't have science courses. What we had, there was no biology, no chemistry, no physics. What was taught in university was literature, language and literature, medicine, several kinds of engineering, so theology, philosophy. But then in the end of the 19th century, there is a turning point where a reform of the university began in the Weimar Republic, which became eventually part of Germany, reframed the universities and put the natural sciences, the basic sciences like biology, physics, and chemistry into the curricula. And suddenly, there were biologists being educated, chemists being educated, physicists being educated. And they also divided these institutes for the basic science in several departments, which contributed a lot to the fragmentation of scientific knowledge along the 20th century. But then we ask, but why? Why suddenly this happened? There was no coincidence about that. Governments and dominant groups in the society, given the role that science had in the 19th century, science changed completely our way of life in the 19th century and was up to the Third World War. There was a very hopeful view about science, that science would make necessarily our lives better. Well, it was easier to think this when you were in the British aristocracy sitting in tea rooms talking about science than if you were a worker in the charcoal mines that were needed to feed that society. You wouldn't think that science was giving you such a great life because you are dying at 30 years of age because of the consequences of exploiting charcoal given the Industrial Revolution. So it depended a lot on where you were in society. But the groups who were making decisions, they were completely astonished about the consequence of science. And we are talking about a system of production and consumption based on profit. And so science was the great bet in making profit, the great bet in making war, the great bet also in reforming society. So governments needed science. And for this, they need to create an army of researchers. It was not like having one Darwin, one Huxley. It was about having thousands of workers, thousands of researchers. Probably none of them would be like Darwin, but doesn't matter. Because the role of the scientist changed completely. The science became a new kind of proletarian, a new kind of worker, a very skilled worker that needed a lot of education, but was a worker. And what happened to this work? It was alienated from the very process of producing science. In the second half of the 20th century, emerged a kind of thing that didn't happen before. You could be a very successful science without having a clue about how science works. If you dominate a method, you can publish hundreds of papers. You are very good at the method. Nobody can run that statistical method as good as you. You publish 10 papers per year, 20 papers per year. But what you are doing, you are running a method. You are not thinking the research question. You are not interpreting data. You are simply running methods. So it became so technical, the work of science, that there was a room for someone who didn't have a room before. There was a completely skilled technician who was a very good worker, but was completely alienated in relation to the nature of science. This is an extreme case when taken as a perhaps caricatural example of how technical science became when it became part of a production system. And we accepted this. Scientific knowledge production became industrialized, papers and papers and papers and papers, like a mass production of papers. We became more alienated workers. And the best thing when you want someone to get the job done is someone that doesn't think too much. Because when you think too much, probably you don't get your work done so efficiently. The time you are running a method, you are thinking about, well, is this really a good research question? Well, you should run your method. And just to complete this answer, we who works in public universities, I think we are completely misguided about what's science in the world. If you go to the OECD website, look for a report on scientific and technological production from 2015, and you get there the following data. 60% of the funding for research and development, scientific research and development in the world in that year, and that was the last time I saw these statistics, was paid by private companies. 60%. Most of this work is not people in public universities being funded by private companies. No, most of this work is the research and development departments of private companies. Is someone doing research not to understand nature, but to produce a drug, to produce an engineered tomato, to produce a new robot? That's we are talking about something completely different from doing science as you usually think about doing science. We are the minority. People who are at the public universities or public research centers doing publicly funded research, we are the minority. And interestingly enough, we talk about science as if we were the majority, which, which I think it is a symptom of how alienated we are generally about what it is this big enterprise called science, of which we are part, but we are not really understand the whole machine in which we are embedded. And I think we should understand this, so that we choose where we want to stay in this big machine. I want to stay in this big machine, cracking the machine. That's what I wanna be. I wanna be there, trying to show, well, perhaps we should do something more when we try to do biology than just produce a new engineering tomato. No problem building an engineering tomato, but what do you understand about nature by doing that? If your goal is just, well, doing engineering tomato, give me a lot of money, well, you are exactly the alienated worker they want you to be. I'm a bit harsh on this, but it's okay.
Thank you so much, Professor Charbel. Your last answer was really excellent, intriguing, and also scary for us at the work of science. Yeah, so we have no more questions. Thank you so much, Professor Charbel.
Thank you for the attention, for the invitation, and when you want, we are here. If we find a slot in time, I'm always available.
Chado, thank you very much for your speech, for your answers. And this discussion is extremely important to us. And I think we will recommend your discipline or set of disciplines that you gave in the University of Bahia to our students, because it will be fantastic to our students.
Please do so. If you remind me by email, I can change all the programs. And now is the middle of the semester, but for the next semester, one good thing about teaching remotely, now in my course I have students from several different universities, which is a great thing that's not possible when you're physically teaching. It's one good thing about remote teaching.
One thing at least.
One thing at least.
Okay, thank you, Chado. So
okay, bye-bye. Thank you for the attention.
Thank you.
Bye.
Wow, it was mind-blowing to me. I take several notes here to discuss, but we have a scarce time now. Now we'll have a lunch break, and we will return at 2 p.m. with the speech of the Professor Paul Fine from the University of California, and after 3 speeches in a part of the talk session of the PNPGs. And that's it. So have a good lunch, and we will return soon. 2 o'clock.
Okay.
Pode começar, professor.
Danilo, você está com o seu microfone ligado, você viu?
Pode começar.
Okay. Good afternoon to everyone. After this lunch break, we will continue the activities of this third symposium on comparative biology. We have some activities this afternoon. First, we have a lecture of Professor Paul Fine, that is from Berkeley University, that will be introduced to Professor Tomás Ferreira Domingues, that is here. Tomás is the vice coordinator of our program. And after the lecture of Professor Paul Fine will be the section of the postdoc from our program here in the comparative biology. First of all, I would like to say you that if you are in YouTube and you could take photos of you watching the activities that we are doing and post it in the Instagram and Facebook and other social media, it will be amazing as an advertising to our program. Okay, thank you very much. And as usual, if you have comments, if you have questions to Professor Paul Fine, please put it in the chat. Okay. Tomás, I'll pass the floor for you to introduce Mr. Paul Fine. Thank you very much, Paul. Tomás, your microphone.
As always, there are some mistakes. Hello, everybody. Good afternoon. Welcome back for this afternoon session. For me, it's a pleasure to introduce to you Professor Paul Fine. Paul is a friend, is a colleague that was at the same place I was during our PhDs. Paul was there a few years before me, and he left for straight to Berkeley, right, Paul? After your PhD?
I don't know. It's so long ago.
Anyway, Paul is now a professor at the Integrative Biology Department at Berkeley University, at California University. And he's been working with the flora of the Amazon for many years now. Big specialist and likes to be in the field, likes to have a beer with the students in the afternoon. And in the meantime, he studies evolution, habitat specialization, but he has huge experience with protein genes of tropical plants. So, welcome, Paul. Take this opportunity to make people more interested, even so, in the Amazon.
All right. Muito obrigado, Tomás. Eu falava um pouco de português, ou portunhol, melhor, antes da pandemia. Mas 1000 horas no Zoom mataram muitas de minhas células cerebrais. Então, I'm going to continue in English. But I think you guys are doing a lot of work in English, right? About presentations and your writing. Mm-hmm. So, and I'm sorry about that too. I didn't make the system.
No.
If it was up to me, we would all be doing Brazilian Portuguese all over the world. It's a much more fun language. So I'm going to try to present my my screen here. All right. Tell me if it's working.
Yeah, it is.
Okay. All right. So I'm going to tell you about some work that I've been doing for the last, more than 5 years, a big project with lots of people. And my main collaborator is Diego Salazar from Florida International University. And there's been a team of people from Peru and Manaus that have been working with us on this project. So from Manaus, Fabricio Baccaro especially, and Emerson, Marcelli, Carlos Nogueira, all from Manaus, and then from Peru, Italo, Magno, and Milagros. So this is a very long project involving lots of people. And what is it about? Well, we are trying to understand chemical diversity in plants. And plants can't run away, right? When something threatens a plant, it's pretty much stuck right where it is, rooted to the ground. So what do they do about that? Well, plants have a lot of ways to defend themselves. And I know that all of you who like to eat food are familiar with the ways that they defend themselves, because these things often end up becoming flavors and spices in our foods, right? And these chemicals, they usually in the literature, they people call them natural products. They call them plant secondary metabolites. Secondary meaning not primary part of photosynthesis, but secondary, something secondary function. I like to call them chemical defenses. And basically, the theory of the evolution of plant chemical defense diversity hasn't changed very much in the last 50 years. The main theory is from this paper in 1964 by Ehrlich and Raven about butterflies and plants. And in this paper, the authors describe this evolutionary arms race, where let's say a plant evolves a new chemical, and that new chemical gives it an advantage where all of a sudden, let's say the butterfly can't eat it anymore because it's got a crazy new chemical that is totally toxic to the butterfly that likes to feed on this plant. Well, if that were the case, this plant would spread its range and have a big advantage and go all around and undergo allopatric speciation. It will go in new places, in new habitats. It'll cross rivers, it'll cross mountains, and it will experience irradiation and become a very common and dominant plant. Well, eventually, according to this theory, the insect will evolve some counter adaptation where it can detoxify this new compound the plant has. And then that insect all of a sudden has all this food it can eat. And it'll increase its numbers, it will spread its range, it'll go and eat this food everywhere that this plant lives. It will cross mountains, it will cross rivers, and it will go to new habitats, and it will diversify and have its own radiation. And this process is theorized to repeat again and again and again. And the evidence that they had in this paper was just that many genera of Lepidoptera and genera of plants are associated, so that you have lots of specialization and lots of caterpillars only eat one genus of plant, and that the plants often have similar chemical defenses. And so this theory is it's thought of as to be a pairwise interaction of one adaptation followed by a counter adaptation by the insect, followed by another adaptation by the plant in a pairwise manner. But we know that real life is different. Real life is actually much more complicated. And when you think about it, most plants that we think of don't just have one kind of butterfly feeding on them. They have lots and lots of different enemies. And so they have lots and lots of different chemicals as well. And so these interactions are very complicated. And Dan Jansen wrote about diffuse coevolution as a way to understand these interactions and the way that plants evolve. And so that's what we want to think about today, how to understand chemical diversity in plants. And I will remind you that most of the work that's done on chemical diversity has really been on just a few plant species, maybe just a few specialist herbivores, and then they study how the chemicals have changed through time using just a few different kinds of chemicals, a few different secondary metabolites. But what we wanted to do in this project was look at lots of species. We wanted to look at all of the insects that are feeding on them, and we wanted to look at all of the chemicals that the plants were using to try to understand the evolution of chemical diversity. So, and I just said this, we were trying to study everything in the genus Proteum. And Proteum is a genus, in we say Proteum in Brazil. It's got about 200 species in the genus. Probably about 150 of them are in South America. In the Amazon, especially diverse and common. So in where I work in Iquitos, Peru, you can find 50 species of Proteum just in a few hectares of forest near Iquitos. And in Manaus, it's also the same thing. Very common, very diverse. I think at Reserva Duque, the most common plant is Proteum hebetatum. So, but there's also probably 40, 50 species that you can find in the forest. And they produce a lot of different kinds of chemicals, but and they're very famous for their resins, the terpenes. The word that people use for in many parts of Brazil is breio, and breio is also a kind of a resin that people sell in markets, and they use for making incense, or they use it medicinally as well. And I've been studying this for a long time, and trying to collect Proteum from all over the world and make a phylogeny. So we have a good taxonomic basis. We have a good phylogenetic basis for comparing the species and knowing which ones there are. And a lot of this work has been done with my friend Douglas Daly, who has spent a lot of time in Brazil. Maybe some of you have met Douglas, Douglas, as they say in Brazil. And he and I have worked together very closely on Proteum. So today I'm going to tell you about our work to understand chemical diversity in Proteum, and also the work to understand what the herbivore communities are. And then the more complicated part is to try to connect the chemicals to the individual insect herbivores, and to understand which chemicals are especially important. And then finally, if hopefully we'll have time, I'll tell you about a comparison across Iquitos, Peru, and Manaus, and how the chemicals and insects change across geographic space. So I'll start with just a reminder about tree diversity in the Amazon. We don't know how many species of trees there are. Probably somewhere between 16,000 and 25,000 species. But this is, the highest concentration of tree species in the world, in the Western Amazon, in the Central and Western Amazon. And one of the reasons that people say there are so many species is because of the biotic interactions that have been occurring over long periods of time in the Amazon. And the idea is that you have these really intense biotic interactions in tropical environments without any seasonality, that the interactions continue. There's no escape for the plants during the entire year. And there's also lots and lots of food and lots of insects. So there's more insects, more intense interactions that don't stop, and that this is an evolutionary pressure that is much stronger than other parts of the world, and that this may be contributing to diversification in the Western Amazon. And one way that this could be happening is this theory of the geographic mosaic of coevolution, where you might have different, let's say you have different plants and different enemies that are eating the plants in different places. So you have selection happening in different ways in different parts of the plant's range. Just to give you a little cartoon about this, imagine, these are just some of the different kinds of chemicals that plants produce to defend themselves. And some of the common ones here are, maybe you've heard the term tannins before, phenolics. That's what you find in tea or in wine. is that bitter, the bitter phenolics. And then imagine another kind of chemical, a flavonol, for example. And let's just imagine that, you know, a coleopteran and a hemipteran are affected by different kinds of chemicals. And this is reasonable to think about too, because different insects have different gut pH, and they respond differently to different sorts of chemicals. So imagine you have a plant that has some kind of geographic range that's outlined in green here on somewhere in the Amazon, let's say. And let's say that there's one species of hemipteran that eats this plant only on the western part of the plant's range. And let's say there's a beetle that eats the plant in the eastern part of the range, and there is some overlap in the middle. Well, you could imagine that different chemicals would be selected for in different parts of the plant's range. And that if something were to happen, let's say the plant, you know, maybe through climate change over the years or too much herbivory, the eastern plant and the western plant became separated from and isolated from one another. You could see how you might have from one species of plant, two kinds of plants would come. One that would be expressing more, say, terpenes, and one that was expressing more tannins. Different chemicals responding to the different enemies that were attacking the plant. And so to understand this, if this is something that actually happens in nature, we need to know more about what are the enemies that eat plants. How specialized are they? Do they, and then what kinds of chemicals do they interact with? Do the plants have lots and lots of different chemicals, and how do the chemicals match up to the different insects that are attacking the plant? And how does that change in different places? And we would predict that if you had a large geographic range, the plants would have different herbivores in different places, and they would express different chemicals maybe if they were being eaten by different kinds of insects. And then we would expect this sort of local adaptation to occur, where different insects assemblages are selecting for different chemicals in the plants. So here's the Amazon basin, and lots of different kinds of habitats and forests. And this is where we've done a lot of work over the last decade. And so I'm going to first start with chemical diversity, and I'm going to start with Iquitos, Peru here on the Amazon River. And I've been doing my work at this reserve here called the Alpahuayo-Mishana Reserve, which is just about 25 kilometers to the southwest of Iquitos, Peru, on the Amazon River. And I know in Brazil you call this the Soimoes River, but in Peru, it's the Amazon. Okay, so what we did was we sampled 32 species of proteum, and we looked at, we marked 25 individuals of each species, so about 900 total plants. And we visited these plants at least once a week, usually more, for 64 weeks. And we collected every herbivore that we saw eating the plant, not just sitting on the plant, but actually eating the plant. We did DNA barcoding of all herbivores, and then we collected leaves from the plants, and we did the chemical analysis of the leaves. And this is just a graph of where all those 900 plants were in the Alpahuayo-Mishana Reserve. You could see they're distributed in throughout this about 10 hectare area. So we did a lot of chemical analysis. And I'm not going to go through this, but this was work really done by Diego Salazar, who's a very good chemist and a very good ecologist. And we found lots and lots of different kinds of compounds, hundreds and hundreds of compounds. Most compounds were phenolics or tannins, but there were lots of terpenoids, including these volatile compounds like monoterpenes, sesquiterpenes that are components in the Breu resin. Also triterpenes, phytosterols, and phenylpropanoids. So lots and lots of different compounds. When we took all those compounds and we looked at the phylogeny of proteum, we found that there was no real phylogenetic pattern, that close relatives often had very different amounts of chemicals, but also different types of chemicals. And you can see the different types of chemicals are colored in the top. But that being said, the genus Proteum has, a similar palette of chemicals that they have. They have a lot of phenolics, saponins, triterpenes, mono and sesquiterpenes. So all of the species tend to have some mixture of all of those, right? And you see, for example, there's no nitrogen-based compounds in Proteum, right? No alkaloids, for example. So Proteum have a similar kind of chemicals for all species, but within the genus, there's no pattern in terms of close relatives generally don't have very similar chemicals. And so when we did a test of chemical similarity with phylogenetic similarity, we did not find any kind of result. And that, I'll tell you, is maybe not what you would predict with Ehrlich and Raven's coevolutionary arms races hypothesis. Because in that theory, you have sequential evolution of similar chemicals. And you might predict that close relatives would actually be more similar in chemicals. And I'll come back to this a little bit later. All right, what about the insects? We caught lots and lots of insects, all sorts of different ones. We had a total of 4,500 different feeding records. And we caught more than 210 different herbivore species. Most of these were hemipteras. The next most common was Lepidoptera and Coleoptera. If we looked at the 85% of all the feeding records, we found that there were 50 of these 200 herbivores that accounted for most of them. And so we didn't want to keep in our analysis herbivores that we only caught once or twice. We wanted to have herbivores that seemed to be associated with the plant. So this is a graph to look at whether or not we found a lot of specialists or generalists in terms of insects that are eating Proteum. Now remember, specialist and generalist is a kind of a relative term. So you could call all of them specialists if they only eat Proteum species. But within Proteum, how many species of Proteum do they eat? On average, they ate about 10 different species of Proteum. And you can see this insect down at the bottom that has a very large black bar. It ate pretty much every species of Proteum. So most of the herbivores that we found ate lots and lots of different species. But that doesn't mean that they just ate, there was, random, no preference at all. When we did an analysis, a Poisson analysis, to ask whether or not certain insect species, were they associated with different species of Proteum, we found that there was significant attraction and repulsion, meaning that some insects were significantly associated with some species of Proteum and not with others. And we think that that has to do with the chemicals. And I'll tell you a lot more about this. So how do we associate chemical richness with herbivore species richness? And this is richness and abundance. So we measured how many different kinds of chemicals the plants had, and we measured how the total weight of chemicals that they had in their leaves. And I'll remind you that plant secondary metabolites can be a very large investment for the plants, up to 40% of their dry weight. So it's a big deal for these plants to produce these chemicals. So the first thing we did was a very simple correlation. We wanted to know if herbivore richness, diversity of herbivores, or herbivore abundance in terms of feeding records, did it correlate with the diversity of chemicals that the plants had? And we found a very strong relationship. Every blue dot here is a different species of Proteum. And so every dot has a number of herbivore species that it's associated with it, and a number or a weight of secondary metabolites or chemicals. So that's good. And the next thing that we found, we looked at whether the chemical abundance, so amount of chemicals, was also associated with herbivore richness and abundance, and we found that it was. So chemical diversity and chemical abundance. So total investment was also important for being able to predict how many different species of herbivores and how many different feeding records were found on each species of Proteum. Okay, so that's good. That suggests that plants are under selection to have a diverse number of chemicals and also to have a lot of chemical investment to protect themselves from being attacked by lots of herbivores. But what about, can we understand which chemicals are associated with which insects? That is the complicated thing. And we predicted that there would be some metabolites, some chemicals that would be very, very valuable. And that these valuable chemicals, we would find them more often in Proteum compared to chemicals that did not do any effect for repelling herbivores. And the way to do this was to figure out, because you can imagine that some chemicals are going to be repelling some herbivores, but attracting others. And so we wanted to figure out a way to look at all of the data all at once and figure out the average effect across all interactions. And so, yeah, we predicted that we would find that the effective chemicals would be found in more species of Proteum. So how do we do this? Very difficult because it's just too much data. We have 50 different herbivore species with different preferences. We have, in this data set, 460 different chemicals. And this is a huge matrix of data with each of the 32 species of Proteum. So we use machine learning, statistical learning called least absolute shrinkage and selection operator, a LASSO. And this uses 40% linear regression, 40% model selection with the Aikike information criterion, and 20% brute force attack, which is, I think, a joke from Diego. And it's something that people use in genomics to determine which genes are associated with phenotypes. What happens is you take the data, you take a subset of the data, and you search for models that predict herbivore feeding rates based on chemistry. And then you use that on the remaining data to test which metabolites are not improving the model. And then you reject the chemicals that do not improve the model, and you repeat until the model cannot be improved. And this is kind of what the matrix looks like. And you imagine you have chemicals on the left and herbivore species on top, and you sum up the positive and negative interactions across. And then you come up with a net selective value to see how effective each chemical is. And what we found was that in our data set, 84 different chemicals had an effect on herbivore feeding preferences. It's about 18% of all of the chemicals. We're going to call those LASSO chemicals, or herbivore effective chemicals. We found that every species of herbivore was affected by at least one of these chemicals. Most of those chemicals affected multiple herbivores, and many of these had contrasting effects on herbivore feeding preferences, where they were repelling some herbivores but attracting others. And so remember, we were predicting that the effective chemicals would be found in more species of Proteum than ones that were not effective. And here's the data. If you look at the number of species of Proteum on the bottom, and then if a chemical is effective, it has a positive number, and if it doesn't effective, it has a negative number. You can see that only the effective chemicals were found in lots and lots of species of Proteum, fitting our prediction. We also found that the number of species that had these LASSO chemicals had less. They invested more of their resources in effective chemicals, which makes sense. And the plants that had more of these effective chemicals were able to actually invest lower total chemicals. So they were able to save energy by having more effective chemicals. And then when we did a phylogenetic test of these LASSO chemicals, we found a significant result. Actually, kind of more in line with Ehrlich and Raven's coevolutionary arms race. So not with all of the chemicals, only with the effective chemicals. So we find that this is all of this together is strong evidence of the role of multiple and contrasting selective pressures on the evolution of Proteum selective metabolites, and that the chemical diversity evolves probably from diffuse evolution, diffuse coevolution. And you don't need to have a lot of specialists. You can have generalists driving this as long as there are strong preferences. we found that each plant species had at least one lasso chemical. Each lasso chemical repelled less than 5 herbivore species. So it doesn't, one really good chemical doesn't work for all of the herbivores. There's no magic bullet. You can't just have one kind of chemical. You need to have lots of different ones to be able to have the most protection. And this reminds us of something that was written over 1,000 years ago by Sun Tzu, a Chinese philosopher. He says, "One who has few must prepare against the enemy. One who has many makes the enemy prepare against him." So if you want to know more about this study, this was published 3 years ago in Nature, Ecology, and Evolution. The paper is called Origin and Maintenance of Chemical Diversity in a Species-Rich Tropical Tree Lineage. What I want to tell you about now is what we've done since then to try to compare what happens when you look at herbivore and chemicals between Iquitos and Manaus, which are about 2,000 kilometers apart, or maybe 1,500 kilometers apart. Remember, we were thinking that if you have large distances, that there are probably different herbivores in different places, and that should cause selection for different chemicals. And that might be in line with this geographic mosaic hypothesis. Here's a look at where we did the study in Reserva Duque and Reserva Campinas, north of Manaus. And we did the same thing where we collected insects and leaves for chemical analysis. We did the same thing with DNA barcoding to look at which insects were attacking the plants in Manaus. And there was a little bit of a difference between our methods. We had less time and less money in Manaus. So we had fewer species that we could monitor. We only looked at 14 species in Manaus. But what's really interesting is that 12 of these species are the same species that were in Iquitos. So we've had 966 feeding records in Manaus, 163 insects, and there were no single specialists in Manaus. But remember, only 14 species were looked at. We looked at a phylogeny of all of the insects. And what's interesting about this is that if you look at H6 here on the right, the most common insect in Iquitos and the most common insect in Manaus are sister taxa. So that's interesting. And we found this other interesting result where the species that had the highest numbers of insects feeding on it in Manaus had the highest numbers of insects feeding on Iquitos. But what we found when we looked at all of the insects between Iquitos and Manaus, there were no species in common of insects. It's completely different insect fauna in Manaus than Iquitos. And yet, we found that species that had a lot of insects eating them in Iquitos also had a lot of insects eating them in Manaus. But when we looked at which insects were eating which, the community of Proteum, we found that although there were also hemipterans, coleopterans, and lepidopterans, there was a lot of difference between which kinds of clades of insects were eating the individual species. And this graph is very confusing, but what I did was I took each of the 12 species in Iquitos and Manaus, and I put them next to each other, and I colored the numbers, the relationships of the herbivores that were eating them. And so blue, for example, is one clade of coleopter. Okay, so I guess what I'm trying to look at in this graph is, even though all 100% of the insects are different in Manaus and Iquitos, you could imagine that what if it's just very close relatives of those insects are eating those same plants? In that case, you would expect a pattern of colors very similar amongst the pairs of species. But that's not what you see at all. You see completely different kinds of insects are eating the same species of plant in Iquitos and in Manaus. Another way to show this is just to do some community phylogeny similarity. And you can see On the pink is all Iquitos, and the blue is all Manaus. So in general, the assemblies of insect species between Iquitos and Manaus were not did not follow plant species identity, with one exception. You can see here Proteum opacum in Manaus and Proteum opacum Iquitos are coming out together. So this finding of really high beta diversity, high turnover with geographic distance, is something that we found in another study that we published 5 years ago, when we just looked at insect communities across the Amazon basin. But we found turnover when you looked at different kinds of insects, both with habitat and also with geography. Wojtek Nowotny, though, has done a similar kind of study in Papua New Guinea, where he looked at 2 sites 500 kilometers apart, and he found very low beta diversity. So something different about the Amazon from Papua New Guinea. Okay, what about the chemicals, though? In Manaus, we also looked at the chemical diversity of each of the proteum species, and we compared it to the proteum species in Iquitos. And here they're put together in one graph. And what we were very surprised to find is that the chemistry of the proteum species in Manaus and Iquitos were almost identical. Here's an example of Proteum ferruginum in Iquitos and Manaus, and look at the chromatogram showing not only the exact same peaks, but also very similar in the amounts. So, you know, something about like 95% similarity between Iquitos and Manaus, even though 100% of the insects are different. So I think that's a very interesting result, that the fact that you have the same species richness of diversity of insects on the same species of plants, even though all of the insects are different. What could explain this result? You know, you have completely different insects, same chemicals, and yet the chemicals seem to be doing the same the same effectiveness in Iquitos and Manaus, even though the insects are completely different. And I will remind you from the first part of the talk that we had correlations between chemical diversity and herbivore diversity. And so that's the same thing in Manaus and same in Iquitos. And we also had a correlation between effective compounds, those lasso compounds, with total chemical diversity. And so the implication here is that plants that have a high chemical diversity are going to have more effective chemicals. And if they have more effective chemicals, that'll be good for them, whether they live in Iquitos or in Manaus. All right, to sum up the predictions of the geographic mosaic, we found different herbivores in Manaus and Iquitos, but we found the same chemicals. That was not what we were predicting. And so this geographic mosaic hypothesis, it could be happening, but not in the exact same way that we were thinking. And I think that when we think about what is going on here, it's about having effective chemicals. It's about having the more chemicals that you have, the more that you'll be able to defend yourself against herbivores in different parts of the species range, but also other kinds of things like fungal pathogens, which we're studying now. So anyway, that's what I was going to tell you about today. This is a picture from a field class that we did in the Rio Negro in Brazil in 2014. Some of the co-authors are on this slide. It was a lot of fun. I hope that in the future, sometime soon, I can get back to Brazil and teach another field class, because it was about as much fun as you could possibly have. So thank you. And I'm going to stop sharing my screen.
Beautiful. Thank you very much, Paul. It was very nice to see this much results. Many
Sorry,
hours
too
in
much,
the field. Okay, so I guess we have some questions on the YouTube channel. How do we do that, Milton?
Hi, Professor Thomas. Hi, Professor Paul. Nice to meet you. So I received some question in the YouTube, and I will say his now. This question is from Eduardo Oliveira. he said, can you use the lasso model to predict it for abundance or of plants and herbivores? Because the production of metabolites may take energy that could be used in reproduction, I assume. Or does it actually improve fitness?
That's a great question. I think, yeah, I presented some results that said that plants that had more effective chemicals were able to invest less total investment in chemistry. And so the implication is that if they're investing less in chemistry than other plants, then they should be getting an advantage and they should be able to use that extra energy for growth or reproduction. The one thing that we haven't done that I'm hoping to do next is get a good idea of how these chemicals translate into plant abundance. So, and that's a difficult question to ask because when you think about plant abundance, it's something that is difficult to measure at the right scale. You know, you would need to measure this at a local scale, but also at some kind of larger scale, because the prediction would be that, you know, plants would have lots of individuals in a larger geographic range if they had more effective chemicals. And so that's what we're trying to test next, and we're trying to think of smart ways to be able to ask that question. But I think you're right about the idea that plants that have more effective chemicals should be able to use that energy for other things and translate into higher fitness.
That's great. Thank you, Professor Paul. I also have my own question. So I usually work with fireflies. And nowadays we know that some of them are carnivorous, but sometimes before some of species were herbivorous. However, we checked some of them, of course, the evolution of the luciferase enzyme has as the ancestor the 4-coumarate ligase, which seems work with coumaric acid and detoxification events. You think when you work with those species that change from herbivory for carnivore, those other compounds that can work as defense can change, or they just keep on the species for a long time during the evolution?
I don't know, but I will say this. One thing that we would like to study, which is similar, is how insects can sequester compounds and use them for themselves. And I actually think this would be not that difficult to study in our study system. We've thought about it because if you think about it, sequestering a compound from a plant and using it is like the plant's worst nightmare. You know, the plant spends its energy on a compound, and not only does it not work, then it's used against them because it works for the herbivore to defend itself against a predator that would otherwise maybe help the plant out by eating them. So, like, thinking about sequestering is very interesting. And I think what we could do is we could collect the insects and we could run them through the same chemical process to see to what extent are the insects taking those chemicals and modifying them, or are they just using them, you know, for their own defense? Yeah, I think sequestering is really interesting. You know, like, I think sequestering actually goes with the evolution of specialization in a way, right? And maybe we wouldn't find it so much because we didn't find so many specialists in this system. But anyway, I could talk more about this, but let's get to a different question, I guess.
Okay, Professor. Yeah, excellent idea. Maybe you can do this in the future. It'll be very interesting. Thank you so much.
Yeah.
Let's check if you have many more questions on YouTube.
While you check that, I will ask my own question as well. Okay. So how long it took to get all this data on insect feeding on the protein species? It was a year or 5 years? Does it change year to year? That's what I'm trying to answer.
Yeah, that's right. Well, we did first we did a ketose, and that was 64 weeks, so a little over a year. And then we started it in Manaus, and we did that about a year. So that's we did that over 2 years, but in 2 different places.
Yeah, but I think from year to year, the number of different species of herbivores, how much would vary?
Yeah, I have a little bit of data on that. Actually, I haven't analyzed the data, but there were 2 species that I did another project on that was the same as this that were also included in the second project, where we also in the same in Iquitos we collected data for a different year. So I've been meaning to compare the insect communities, but I think you're right. We know this from insects are very what we say patchy in time and space, and there's boom and bust, and I think that's another reason why these effective chemicals are if you ask why did we only find 18% of chemicals being effective, well, I think it's because a lot of those other chemicals are probably effective, but they're effective against herbivores that we didn't catch. And those herbivores might be in different parts of the geographic range, but they might also just be in Iquitos, but we didn't happen to sample them because they were in low abundance during the year that we were sampling. So I think you're right. Like, it would be great to do this, over a longer time period and measure the seasonality of the herbivore communities.
Yeah, it's long hours for students to be in the field. But it would also help to explain the difference you see between Iquitos and Manaus, perhaps.
Yeah.
And I have another question. Can I go on, Danilo?
Please, Professor Thomas. We don't have any other question chat on YouTube.
Okay. So it seems that the plants have the protein that you showed has the ability to produce a lot of different chemicals, a high variety, and only a few show very stronger efficiency in your case. But do you think this is conserved along other lineages, the Ingas or other families, and meaning that most of the plants are able to express a lot of different compounds, but the amount of compounds produced of each kind might change through time and depending on the stimuli of the herbivorous being there?
Yeah, I think that happens. One thing that we noticed when we looked at the comparing the effective and the not effective chemicals on the phylogeny was that the non-effective chemicals seemed like they were only found in 1 or 2 species. And so what we took away from that is that we imagine that like a chemical gets really effective and it probably has a limited amount of time where it's really good. And then slowly but surely it starts getting dropped off by the plants. They say, oh. And so I think that this happens a lot, but it's a slow process probably. And like you're suggesting, there's only a certain number of combinations that the plant can do. Like, I can't expect that Proteum is all of a sudden going to start making alkaloids, for example, right?
Okay.
Same thing, Inga. Inga does like nitrogen-based compounds. It does like non-protein amino acids and saponins, and so Inga doesn't do terpenes very often. So you wouldn't imagine Inga is going to start doing terpenes, but they have their diversity, and they're going to maintain their diversity, and they're going to keep trying to come up with new compounds. But it's going to be within a limited amount that they have some phylogenetic constraints in the exactly how much diversity they can achieve.
Mm-hmm.
Did that answer your question?
Yes. I don't want to dominate, but I would like to ask another question. If Milton let me.
No, there's another question in the chat, I think. Let me see. From Eduardo. Do you have an estimate of how many of those compounds are volatile? From Eduardo Oliveira.
Yeah, I think about it's on my other graph. I can tell you. Sorry for a second here. Yeah, so we found exactly. There we go. There was 60 different kinds of sesquiterpenes, and about 20 monoterpenes. And most of the monoterpenes and the sesquiterpenes are volatile. So I would say probably about, I'm going to guess about 80 different chemicals are volatile. These are really common in proteome. Those chemicals are shared amongst many, many species. I've done some other work looking at the volatile chemicals. And we did another paper where we looked at the terpene synthase genes, and we looked for evidence of selection in the genome. But we found actually more evidence for stabilizing selection, and the idea being that maybe these volatile chemicals are more like signals to tell predators that herbivores are eating them. In that case, you would predict more of a constant signal and not a diversity of compounds, but just something more stable.
Thank you. I have one question of mine.
Sure.
I remember the day we are many years ago talking about the diversity of protein in the Duke Reserve in Manaus. And I can't remember the name of the species, but maybe a lot of them, maybe 20 or 40 species in a small piece of forest. And I remember that the flowers of the protein are small, and I think the pollination is generally pollination because the flowers are small. Okay, and you were saying that the type of speciation, the sympathetic speciation, caused by biotic interactions, and mainly or emphasized because the compounds that plants can carry. Is that correct? But how this mechanism could work in this case?
Yeah. Well, the work that we've done so far, we find that that I think habitat specialization plays a big role, and that is that you have like, say, sandy soil next to clay soil, or you have flooded forest and clay forest, and you have different biotic communities in the different habitats, and so there could be an interaction between the strategies that a plant has for living in one habitat, and it gets magnified by the insects or the fungal pathogens that are living in that habitat too. So it makes the differences stronger between the habitats. And if you imagine that you have intermediate phenotypes between habitat 1 and habitat 2 are not as fit on either habitat, that could drive selection for habitat mediated speciation. And we found some evidence for that, and that's something that I want to continue looking at in the future. But I also think that climate change during the Pleistocene is another mechanism that moves populations around, and I think that especially with drought and flooding can cause big changes in forests. And you might imagine that you could have some populations that are separated from one another geographically, and kind of more refugia, for example. And I think that could be important. And you could also imagine that different refugia have different assemblages of insects and fungus that also could drive selection. So those are some of the things that I think probably happen, but I think a lot of us just make up stories about this.
Okay, thank you. Well, I think I don't know if we have more questions in the chat. I think not, Daniel. I don't know. Daniel's not here. So I think it's time. It's almost 3 p.m. I'd like to thank you very much for your virtual presence here. Our symposium. It was very interesting to see your work. And it was very interesting to see you again after 20 years in person. We are all getting older.
Yeah.
Thank you very much.
Sorry, Professor, we don't have any other question. Let me check one more time.
Okay.
Just Eduardo Oliveira said, I asked about the volatility because many other volatility are important to other ecological processes, including formation.
Yeah, I talked a little bit about that, like signaling between plants and predators. So there's some interesting work on that, especially with like parasitoid wasps can sense, volatile chemicals. So anyway, it's great to see you guys. Thomas, great to see you again.
Thank you
And
very
I
much.
hope that I'd like to be in Sao Paulo sometime in the next couple of years. So
yeah,
everybody,
anytime you're passing through Brazil, you're very welcome to stop by Ribeirão Preto and visit us. If not, we will probably see each other again in Manaus or ATBC.
yeah. I
And
hope that you guys can get vaccinated soon.
oh, that would be great. I bet you have yours already, right?
Yeah.
Good,
Yeah.
good. Okay, Paul, thank you very much. Your talk was a great fit for our program.
Oh, good.
And let's keep talking. Interaction between our program, formation program, and very
Great.
Okay.
Okay. Obrigado.
Thank you,
Paul.
Bye-bye.
Thank you so much, Professor. See you.
Ciao.
Great, Thomas. Very nice nomination of Paul Fine.
It's great, yeah.
To our symposium.
It's amazing as a person and a researcher as well, of course. He published his first Nature paper during his PhD, and without help from his advisor. So
wow,
he was very independent from the beginning. And I think he finished the PhD, he went straight to the position Berkeley. I think he was very modest to say no, he didn't do a postdoc.
A project.
Yeah. Okay. So we have an interval now, or go straight to the?
Depends on Danilo. Just to announce, now we have the postdoc talk sections with 3 sections. I don't know if Danilo is ready.
Yes, Professor, I'm ready. Don't worry.
Yeah, if you
you can start now because I have to stay on the YouTube after that. So yeah, you can start now. Don't worry.
Okay. So I have a pleasure to announce the postdoc talk section. It is formed by the 3 talks that we have in our program. These 3 postdocs, they are granted by the CAPS agents, and they are a little bit different from those from FAPESP, for example, because they are directly linked to the program, not to laboratory itself. So the first one will be Dr. Danilo Trabuco Amaral, that is conducting our broadcast. And the theme is biogeography and diversification of cactus species in dry diagonal of South America. So if you're ready, Danilo.
Yes, okay.
I pass the floor to you.
Okay. Thank you, Professor, for the introduction. Hi, people. So I just share my presentation with you. Just a second, please. Okay.
All right. If you want, people, ask questions in chat as usual. Okay.
Yes. So let's share. So hello, people, again. Thank you so much, Professor Milton, Professor Thomas, for the opportunity. Also, my colleagues of the organized committee. This is a really interesting symposium until now. Several good talks and lectures, and also very interesting questions. So please, if you also have questions, give some for me. They are really, really interesting. So, Professor Milton says, I'm a postdoc at biology in comparative biology program, graduate program. I'm linked directly to the program, but I'm located in the lab of Professor Fernando Frango, which is also my supervisor, this guy right here. Let's see if I have a pointer. I don't think they have a pointer here, but okay. And can you see my screen?
Yes, perfect, Daniel.
Oh, okay, thank you so much. And if you have any questions, please note my email and you can talk in private if you want. So now I'm located in the Fernando's lab, that is Lagevol, Laboratory of Genetic and Diversity and Evolution. And there we try to work using genomic databases and also bioinformatic approach to study a little bit about the diversification of neotropical region, understand what drives this diversification, the forces that create and maintain this evolution and this biodiversity in neotropical regions. So we mainly use phylogenetic and phylogeographic approach to understand a little bit about conservation genetics and also phylogeny of this group. And if you have any interest about our work, please visit our website, or you can just Google Lagevol and you can find us there, okay? So again, I will talk a little bit about neotropical region. Some of my words will be just repetitions of words of Professor Milton. However, I think that is important to resolve some of these questions. So, as Professor Milton said, neotropical region is really, really rich region, not only in species, but also in biomes. As you can see in this picture from Antonelli and collaborators, 2018, we can observe at least 10 different biomes in the neotropical regions. And another interesting thing, they display different features and characters among them. And among them, of course, you can observe some biotic distinctions, but you also observe some abiotic distinctions. Biotic distinctions like the presence of different species richness in each part of the neotropical biomes. So we have biotic and symbiotic variables involved in this richness of species in this area, this high biodiversity. And the other very interesting thing that becomes neotropical region, very interesting region model of study is the proximity or the relationship among these biomes. As you can see here, you have a very interconnected area, such as Cerrado and Amazons, Amazon and Caatinga, Caatinga and Cerrado, Atlantic Forest. So they are really, really interconnected regions. So they belong that species can, allows that species can interchange these biomes during the life story then. And as I told you before, the neotropic is a very interesting model, not just because of these features, but also different characteristics associated with the geology and climate conditions, such as we can find narrow areas with high heterogeneity. Also, we can find islands really, really near to the mainlands, which can be used to study islands by geographic analysis. We also have different important river dynamics. For example, the Amazon River, Tocantins River, San Francisco, Araguaia, they all have different dynamics, and they're very, very interesting to study. Of course, have the diversification. The recent formation of the issues that interconnected the South America and North America and prolonged allows that the species change from those big areas. We have connections between rainforest and savanna dynamics. So you can identify different characteristics in this ambient, in these biomes that can be, and of course in this neotropical region as a whole, and that can be used as a model of studies. And these different conditions permit that we have distinct environments, of course, a high biodiversity. And one of these high biodiversity that we usually like to study in our lab is the cactus species. Of course, I have sure that some of you in your home have a mug or a bag or a cup or a plate or a flip-flop with a picture of a cactus. Nowadays, these are very interesting brand mark for several groups of studies. And of course, they display very different traits, morphological traits that we observed here, such as the wood, or as we usually call cladodes, can be circular, can be columnar, can be palm form. They have different colors of flowers, different colors of fruit. And of course, I believe that all of knows about the pitaya, which is also a cactaceae. So we have interesting models of stud included, a well-distributed species in all those areas. For example, in South America, you have a very wide genus, the Cereus genus, widely distributed around the SDTF areas, the seasonal derived tropical forest. Yeah. So if you can corroborate both, compare both pictures, you can identify that all these species occur mainly associated with dry open areas in Caatinga, also a part in Cerrado, Chaco, and also in this north, this patch of savanna in the north of South America. And this area species is also interesting because they have a very important approach in the medical and also cultural and social use. And I have sure that several of you heard some about the species Cereus jamacaru, which is now also mandacaru. And you have a very interesting and beautiful song that we also use about the mandacaru. So based on that, we apply this species of Cerrado and Caatinga and other parts of dry open areas to understand how which the biotic and abiotic variables drives the diversification of the open formations in this neotropical area. So in these studies, we use Cereus genus as our model stud, biological model stud. For that, we perform the reconstruction of the biogeographic history of Cereus using DDH data. Is a kind of reduced genomics approach. Some of you that stay in my discipline last week and in the Fernandez discipline probably heard a lot about this kind of molecular marks. Yeah, and these molecular marks were generated by Juliana Bombonato. She was our master student in this program. Nowadays, she's working in another lab. We also perform the reconstruction of the ancestral traits and also perform species distribution modeling. So this is our first reconstruction, biogeographic reconstruction. And the main point that you can see here is that the Cerrado is the ancestral area of Cereus. So Cereus has your first occurrence in Cerrado, and after that, he suffers some incursions for different biomes. This point was around 3.7 million years, also something around the early Pliocene. And this period was really, really interesting for this group. For example, in this period, you have the expansion of the aridification in the diagonal area. And you also observe this event of expansion of the aridification 2 times before. The first one was 30 million years ago in the Andes, and corroborate with the origin of Cactaceae family. And the second event of aridification occurred in the desert of North America, which are associated with the expansion of the population and also species of Cactaceae on that area. And so we usually associate with this expansion and diversification of cactus species with the photosynthetic metabolism that occur in the Cactaceae. This metabolism allows that the stomach was closed during the day and open during the night, which performs that this species has less water loss than during the day. Yeah. A second point, as I told before, you can observe several events of colonization dispersion from the Cerrado to other distinct biomes. First one for Caatinga, after that to the southern, to the northern to the South America, after that to Chaco, and also turn to forest. So we have different events of dispersion of this group. And of course, as you can see in this topology, the most of the diversification of the group occur in the early Pleistocene. So if you join all these conditions together, we cannot discuss that is no single cause to explain the origin of manatees in neotropical biodiversity. So we have different conditions that can be explored to explain this origin. And joined to this, those conditions that I told before, we also have some other orogenic and climatic conditions that was important for the distribution of the Cereus group. The first one is the final uplift of the Brazilian Central Plateau and other small neotectonism events that occur to the Andes, that originate the most of the rock outcrops. These rock outcrops, also known as high islands, some of you also know, also heard about that. For example, Chapada Diamantina or Chapada dos Guimarães. So these areas can be observed as ecological refuge for these cactaceous species, and also work as a corridor for this dispersion of these groups to south and north of Brazil. Important point, as I told you before, the manner of diversification occurred in the early Pleistocene, a period where we have a lot of glaciations event. So we have glaciation periods with interglaciation period, and these cycles can influence the distribution of these biomes during this period. And you also perform the second reconstruction geographic study, just in delayed, the Cereus fernambucensis clade. That was the first incursion from Cerrado to Atlantic forest. And in this biogeographic reconstruction, you observe several events of vicariance, dispersion and colonization from south to north until reach the island of Fernando Noronha. However, how species can go to there, how they colonize the Fernando Noronha Island that is almost 400 kilometers from the mainland of Brazil. So basically in geological studies, they identified that the last glacial maximum appeared around 20 million years from now. We have several events of transgressions and regressions of marine and sea. So the sea level was deep in certain periods of the time. And with that, we have some, as you can see in this picture right here, you have some island, all this part of the northern of Brazil. These islands nowadays are underwater, but when you have the regression of marine, we can have the continental shelf exposed, and these islands can work as a bridge from the mainland, to the Fernando Noronha Island. That can be occur some stepstone colonization events from the mainland to the Fernando Noronha Island. So, as I told you, we also reconstruction the ancestral morphological traits of Cereus species. Indeed, this part was made by our undergraduation Isis. She identified some morphological biotic traits, of course, and she estimated the phylogenetic signal of those traits, and identified some of them that can be associated with the incursion from Cerrado to other biomes, such as the bracts of flowers, the color roots, the hoops, the flower remains, and others. She also performed a PCA analysis, which also clusters some of these clades, which are very similar that we observe in the phylogeny of this group. And she also tested using a MANOVA analysis how this differentiation about trait, this trait variation, differ from the species occurrence or the relationship, phylogenetic relationship on them, if they are associated with clades, or if some bioclimatic variables can be associated with them. Of course, you identify some strong relationship among the clades and the trait variations. That means that the phylogenetic relationship among those clades are conserved, and the traits, morphological traits, are associated with them. However, you also find interesting signal in a specific bioclimatic variable. That was the bio4, that is the temperature seasonality. That means that the seasonality of temperature is also important to identify and describe this variation among traits among these species. We also performed distribution modeling of these species. We used 14 species of this group that comprise 25 species, and used 4 periods, all of them in the early Pleistocene, from the 800,000 years ago to current. And We overlap these periods after the modeling process. You identify some refuges of Quaternary, such as told before, Chapada Diamantina, Chapada dos Guimarães, Cerros in Bolivia, Serra dos Órgãos in Rio de Janeiro, Turapanga and Mandona, that is a high area in the Argentina. So these high islands are very complex topography that can be associated with different or distinct substrate and climates. Among these substrates, you identify some species in sedimentary soil, in karst soil, calcareous soil. So there are different conditions in different soils that can be adapted, that can be adapted to stay suitable for during these controversial periods of oscillatory glaciation. And also, these highlands in these rock outcrops can serve as a diverse centers. So from them, these species can disperse through other biomes and to other distinct areas. I'm sorry, I forgot to say that all this modeling was performed by other undergraduates of our lab, João Oliveira, and he performed all this analysis. And the last thing that we performed a specific analysis using species cereus examples that occur among the cotton of Amazon and Caatinga. We observe a high instability of this area. We cannot identify a possible refuge on those areas. However, you can identify some possible corridors that connect the the north of Atlantic Forest to the Amazon and also to Caatinga. Those results of modeling was also showed to other species such as birds and reptiles. So here we just corroborate of this analysis. So to conclude this short presentation, and of course this short call to you looking for our lab, there's a very interesting test to be performed as, like bioinformatics studies that I loved. So please contact us. So to conclude our presentation, the Pliocene was the beginning of diversification cereals, as I told before, around 3.7 million years. However, the most of diversification occurred into the early Pleistocene. The Cerrado was identified as a diversification center of cereals. This discussion is really, really interesting because we have several studies suggest that the Amazon or the Atlantic Forest is a source of species diversification. However, you also have some species that occur in Cerrado. Cerrado was also a very endemic region, very important for geographic studies. We also identified that different conditions may act together to perform this diversification distribution cereals group. Some of them are associated with orogenetic change, climatic, and also marine transgressions. We identify some traits associated with incursion from Cerrado to other biomes, as I told you before. Some of them are really interesting. However, I didn't told, but some of them was more predictive in the Caatinga area. A very high association among trait interchange of traits among Cerrado and Caatinga. And the last topic is identify some possible refuges of quaternary and instability between Caatinga and Amazon. That was interesting, mainly because we can now work and look around, face just all these localities, like the Chapada dos Guimarães, Chapada Diamantina, that could be a very interesting areas of study, and also understand a little bit about the instability of the Amazon and Caatinga ecotones. So I'd like to thank again the organizing committee, all my colleagues, especially Professor Milton and Vera that worked so hard, bring all the effort that's possible to become this symposium real. Of course, the people of my lab that was really, really nice people that we also interchange knowledge every day. And despite we are far, far away each other, but we usually talk a lot about our studies. Also, the co-authors of this work, the Professor Zapp and Taylor, both are cactaceous taxonomists. Professor and Dr. Darren Eaton, that is a bioinformatics in Columbia University, and also Juliana Bobonato, a master Juliana Bobonato, and she is our master student in the comparative biology graduate program. Also, the CAPS in FAPESI for the financial support. People, any questions, suggestions, please ask me, send messages. Please, this is my email, this is the lab site. If you wanna find us, Google Lagevol and look for us. Okay, thank you so much. people.
Okay, thank you, Danilo, for talk. I don't know if there are questions in the chat.
No, we have no questions. No.
Questions? Okay.
I'd like to just say two words. The first one is I was responsible to upload the videos of the students, and I would like to say that was a really pleasure to know that all of you worked so hard to prepare a very good videos. We already have the scores of the videos, and all the scores are really close on each other, which means that the quality of the presentation and also the formation, the way that you do this presentation was really nice. So congratulations. And a second thing, I would like to thank you, André, because he prepared a very good abstract book that I believe that all of you are able to download. So thank you, André, for that. And thank you, Professor Milton.
Okay. Danilo, I have one question for you.
Oh, thank you.
We have 5 minutes, I think. You told us, thanks for your speech, first of all. You told us that Cereus fernambucensis is a species that occurs in all the Brazilian coast. Is that
Yes.
right? From northeastern Brazil till Rio Grande do Sul, maybe?
Yes. No, maybe a little Paraná, south of São Paulo.
Mm-hmm. And this species occurs also in the Fernando de Noronha.
Yeah, indeed, it's a peripatric species. The name is Cereus insularis, that becomes from Cereus fernambucensis, that occur in the Fernando de Noronha Island.
Mm-hmm. But the hypothesis is that with the integration or the regression of the coast, it is possible to get a contact between the island that is much more coast. I don't know if it's the correct to say that, to the coast than we have today, because some steps of island between the island of Fernando de Noronha and the coast of Brazil, right?
Exactly.
And why it's not a long dispersion event? Because the fruits in cereals, they are eaten by birds. They adore the fruits of cereals. Why this is not an event of long dispersion?
Yes, it's a very good question, Professor. So now we are, indeed, this work was submitted to the Journal of Biogeography, and we now submit another, we are almost submitting another work from Cereus insularis, that was, the first author is Fernando. And we also developing another work, this postdoc of Fernando in Eaton's lab. And all of this data shows some interesting results. So first of all, we have some introgression from this north and the Iceland. It's really interesting. And the microsatellite markers show that we lost the connection of these groups at least I don't know, a long time ago. We don't have exactly the time, but they lost. So a question that we are using the discussion of this this paper that we are submitting maybe in the few days, that is possible also. We have dispersion, long dispersion, and also we observe some possible dispersions for other species to Fernando de Noronha. So that as a discussion, Zap and Taylor works, they said that another research take a picture of different cactus species that's insularis in Fernando de Noronha, and the discussion that could be another species called Cereus jamacaru that goes to the north of Brazil to there, is a long distance event. Maybe a hybridization of Cereus fernambucensis and Cereus insularis. So it's a possible tool. We identify some questions. Maybe the next we have more concise answer for this question. But for now, we cannot completely say no. We don't have long distance colonization. We are also looking to that.
Okay, Daniel. Thank you very much.
Thank you, Professor.
Any more questions, people? No? Okay, Danilo, thank you.
Okay, thank you. Bye-bye.
It's very interesting to see the cactaceae. I love the cactaceae and other species of the group.
Okay, thank you so much.
Okay, just a warning. We passed the link of this meeting to the email of the students and via WhatsApp, I think. And so some of the students has entered the room. So if you are in YouTube and you are also a student of the program and receive this link, you can enter the room and be part of the room in this moment. Okay. André, are you ready?
Yep.
Okay. Well, the next presentation will be conducted by Dr. André Luiz Cicero. And André, as I told before, and also Danilo, is the responsible for our excellent drugs. Okay. So if you have some questions, anything wrong, please write to André. He is responsible for the work. No, just kidding. It was marvelous, André. Thank you very much for your effort in doing the book of abstracts. And André, you talk a little bit about his study that deals with carassiform fishes. The floor is. Thank you.
Thank you, Milton. The first question I have is, how you see my presentation?
Mm-hmm. Perfect.
Okay, that's not showing for me. Okay, let's start then. Hello everyone. My name is André, as Milton said. I'm a postdoctor of the Biologia Comparative program, and I work with the professor Flávio Bockman at LIRP, Laboratory of Ichthyology of Ribeirão Preto. I'm developing a research about the anatomy and evolution of the peripheral nervous system in the other carassiforms. Okay, here. So for those that don't work with fishes, the main questions is, what is a carassiform fish? You certainly know several representatives of this order of fish. You just did not know about its taxonomic classifications. Let me show you some of them. I'm sure you recognize them. Okay, here are some of the representatives. You certainly know them. Some of these representatives are of very importance in food, and especially when we observe substances fishing, as the pacu, the traíra, the dourado, and other representatives have economic importance in fish keeping, as the tetras. There are a lot of species of tetras, and they move local economies, especially in the Amazon region, as in Manaus and Barcelos, at the region of the Rio Negro. Briefly, in this phylogeny of all living vertebrate, with jaws, the Gnatostomata, we can see the first division here that show two monophyletic groups. Okay, the chondrichthyes, represented by sharks and rays, And the Osteichthyes, basically all the other representatives of Tetrapoda. Osteichthyes, they can be divided into two main lineages. The Sarcopterygians, that include us, and some other fish, as the Piramboia, and all the Tetrapoda. And the Actinopteryges, our point here, that is represented by all known ray finned fishes, the most diverse vertebrata group, that all those groups here. They are represented by more than 32,000 formally described species. The cruciformes are part of a group of fishes known as Ostariophysi. This particular group of fishes are characterized by a presence of an alarm substance in its body. So if a small fish is attacked, for an example, it will release an alarm substance that will produce a reaction behavior by the other small fishes around. So the fishes will know that's time to run. And another amazing feature about this group of fishes is the presence of a Weberian apparatus. This Weberian apparatus is something too similar to our own ears. The Weberian apparatus captures sound vibrations and transmit them through several bone elements, very specialized, to the internal ear of the fish. This feature dramatically increases their hearing capacity. The Ostariophysi, they are subdivided into two well-established groups. Genotophysi, here represented by the gonorrheic. Some of them known as milkfish, all of them marine. And the Otophysi, these remaining orders, represented by 4 orders. The Cypriniformes, some of them known as Carpus. The Gymnotiformes, here are Carpa. The Gymnotiformes, a strictly South American fish order represented by the Poraquê and other electric fishes. The Siluriformes, also known as Bagres, and the already mentioned Crassiformes. So all of them grouped in a monophyletic group named as Ostariophysi. The monophyletic status of crassiforms is under a debate since the use of the molecular data to investigate its phylogenetic relationships. Some of these phylogenetic molecular phylogenies show crassiforms as a paraphyletic group, as you can see here in the E, with 2 African families, the Discodontidae and Cytarrhinidae, with separated from the remaining crassiform families. So, based on all the phylogenies produced until now, we can conclude that there is no agreement between studies, and crassiform is always been reported as a paraphyletic group. The familiar relationships of calciform representatives are also little known. The studies until now agree only with the existence of Anastomoidea, a group of families related with family Anastomide. Here. Also known as piaus or piaparas, os curimbas. The Erythrinoidea, another group of families related to the family Erythrinidae, the Triideas, also is sometimes mentioned, but not always corroborated. So the Anastomoidea and the basal status of Discodontide plus Cytarrhinidae, the two families, the African families, are always shown in the phylogenies, as you can see here, by Cytarrhinidae, Discodontide, and the Anastomoidea. Cytarrhinidae, Discodontide, and the Anastomoidea. So all of them show this. So it's a very solid knowledge. But the position of the other families, its relationship is not understood. It's variating in every phylogeny hypothesis. So despite the economic and ecological importance of the group, we know very little about the phylogenetical relationships in the other Carastiformes. And also, we don't know if it's really monophyletic group. About the morphological studies in the teleosteid, a broader category that includes most of no-ray fin fishes. Most of them are based in osteological features, with only 1% based in neurology. So one of the less studied anatomical complexes in fishes. In the anatomy of the nervous system, and every few of these percentage are about the anatomy of the peripheral nervous system. And that's what I'm trying to do in this work. Just for the knowledge, most of the first studies were performed by the fish sectioning to analyze the peripheral nervous system anatomy. They section in very small slices and stain the peripheral nervous system, and after analyzes the image were mounted. This is a very laborious technique, and so used in very few works. Other studies were made by direct dissection, as performed by Alice in the beginning of the 20th century in many works. It's also a very laborious technique. More recently, Philipsky and Wilson proposed the technique of staining a roll-mounted diaphanized fish with Sudan black B. And some improvements to the Sudan black B technique were made through the time, as Nishikawa introduced the enzymatic process to maceration, and Sang and Parente introduced the concomitant staining of bones cartilages in addition to the staining of the peripheral nervous system. This triple staining technique allows a more precise description of the anatomy, since you have bone and cartilages as reference points. So my work would be based on the methodology proposed by Song and Parent. But I have poor repeatability of good preparations in calciforms. So I fail in reproduce the technique proposed by Song and Parent. And sometimes the species stained beautifully, but most of times they don't stain it at all. So I have no preparations to analyze. I started to dissect the methodology and analyze all the methodological history of the diaphanization process back to Hollister in 1934. One of the first published works in diaphanization of fishes, and probably in invertebrates at all. I concluded that the variations of the quality of the preparations were due to various tips that interferes with the myelin shelf. That's important information that the Sudan black B, the staining chemical, he stains the fat tissue, and the myelin of the peripheral nervous system is a fat tissue. So a lot of the alterations of the steps, time, and amount of reagents were made, and a complete change of the protocols were made. One of them, I start to bleach the specimens. Instead of the use of peroxyhydrogen, I start to use the UV light radiation. The maceration with trypsin tend to generate a lot of microbial infections by bacteria and fungus. So I start to use gentamicin as a prevent of this microbial infection. So we performed so many changes and so many modifications that we propose a new protocol, besides other new methodology to the study of nerves in fishes. So this manuscript, that's mean of publication, is the main result of this first years of the work. Besides preliminary analysis of the material already prepared, we found a lot of new anatomic informations. Not only between carassiform fishes representative, but between almost all families of the three South American orders of Otophysi, the siluriforms, the bagres, the gymnotiforms, the electric fishes, and the carassiforms. So there is a lot of information, anatomical novels that will be published in the next future. And these figures that I will show now to you are some of the preparations made. So here, you can see Salminus hilary, Tabarana, or Dourado Branco, that are prepared with the new protocol. So you can see in red is all the bones pigmented by the alizarin head. These tiny blue elements here are cartilages. They were stained by the ocean blue. And all these black lines, very, very thin black lines here, they are all the peripheral nervous system stained by the Sudan black. Here, the trigeminus nervous complex. And this one, that's a Briconamericus, a little piabinha. You can see the lateral lining nerval all the way. The trigeminals and other, they are very thin and small, so it's not too much photogenic. Here's some close-up of the pictures. Here, the entire bone of the salminos, so you can see all the innervation. Here, the peduncular, caudal peduncle of the salminos. You can see the end of the lateral line nervals and the ramus lateralis accessorios. They run together. All these small lines in black. This all black nerval system stained. Milton just asked how much time does it take to get this material colored this way. Depends of the size of the size and the preservation of the material. So a small fish of 13 millimeters, you spend some 2 weeks. But a bigger fish of 15 centimeters, you will spend a month. But it varies a lot. So here another picture, a close-up of the opercular region, the hyoid apparatus region of the salminos. You can see very evident the trigeminals running for here. Here, the dorsal region. This is a Trichomicterus, a small bagre, a small siluriform fish. Here you can see all the same colors, all the same complexes. So the red is the bones, the blue are the cartilage, and all the black lines are nervous system. And for my luck, the siluriforms and the gymnotiforms that I will show now, they all stain beautifully. The carciforms, not at all. But they stain, and I can do some analysis. So the gymnotiform, the small Engaimania, small weak electrical fish, also stained. So here you can see better the cartilage is stained by the Austrian blue, bone in red, and all the black lines are the peripheral nervous system. And that's a flounder fish, the linguado. The mouth, the 2 eyes on the dorsal region, and all the nervous system of him. It's a very nervous fish. So that is it. So if there is any question. First, I would like to thank everyone here and everyone, the organizing committees who worked very hard. These were weeks of preparation in which everyone put in a lot of effort. So thank you, everyone.
Andrea, thank you very much. I don't know if there are questions in the chat. Are there? Ana Paula or Danilo?
No. Any questions?
Any questions? No questions. Thanks. Andrea, I have a question for you. This kind of preparation that you showed us, they are amazing. And you told us that depending on the length of the material, it takes a lot of time to prepare. Okay, and if you have a student like that, for example, you have at least two difficulties. One is to prepare the materials properly, to put color and etc., and also to analyze the material, because you have to detect the homology of the structures as well.
Yes, that's right.
If you have a doctorate with 4 years, for example, how much materials can you first prepare, secondly analyze to perform, for example, a phylogenetic analysis based on morphological data?
So I hope that with this new protocol that I'm and Flavio Bockman we are proposing, the time will be very more fast than the anterior ones. So will be a reachable aim to analyze a lot of more fish in this work. It's you can done this in a doctoral project. Of course, we will not try to analyze the peripheral nervous system of all cruciform fishes. It's just like the traditional osteological studies. They are very difficult too. It's not so different. The only difference here was the protocol. Since the protocol is established, so you can make this. I'm online or I'm full.
You are online, André. Milton is full.
Milton full. I think that Milton is with some internet difficulties. There is another question for anyone?
No, there's no question.
Okay. So while Milton are come back to us,
I think you can continue with Ludmila, right? What do you think, Ludmila?
okay.
Yes.
Ludmila now.
Oh, no more questions? Okay, Professor Milton is back. Sorry.
Sorry, Andrea. Matt here is coming back. Also to Tomás. Both Tomás and I, we because the internet here. I don't know if the question was recorded. Okay.
I don't hear you.
Oh, sorry. You answered my question. Okay.
Okay.
Okay. Sorry. Are there any questions?
Pelo amor de Deus, bem na hora que vai começar. Vem pegar rápido. Perdão, gente.
Aqui é uma grande família, né? Isso é muito legal.
Yeah.
As pessoas são reais, né? A vida profissional e a pessoal é real.
We will wait a little bit for Ludmila. Ludmila, don't worry. It's totally normal. Everybody with kids in home. Surprises every time.
Yeah.
Okay, I'd like to first to thank André for his lecture, and sorry for the falling system here in USP. Tomás and I was that we were out of space. Well, now that's the last lecture, and we'll be with plants with Dr. Ludmila Micheliu Naspanzarin, that is here, that will talk about the evolution in groups of orchids, the beautiful orchids. Yours, Ludmila.
Thank you, Milton. Sorry again. I start sharing my presentation with you, okay? Just a second, please. Okay. So my name is Ludmila, and I'm a postdoc in the postgraduate program in comparative biology. And today I'm going to present you a little bit of my research about the evolution of some traits in an orchid group, the subtree Oncidium. Orchidaceae family comprises about 7% of the angiosperms, and it's considered one of the largest families of this group. It is estimated that the family has about 20,500 species distributed worldwide, but having a greater concentration and diversity in tropical and subtropical regions.
Ludmila, sorry to interrupt. We can't see your presentation.
Oh, sorry.
Can you see? I can't.
Sorry.
No, yeah.
Don't see my presentation?
No.
No.
Okay. I can try again. You can see that?
No.
No, yes.
No?
No.
No.
Are you clicking em apresentar agora? Button?
What? Sorry. Apresentar agora. Tela inteira. No?
No.
If you want, you can send me by email. I can open here and make the presentation for you.
Às vezes esse problema acontece, daí é melhor talvez a Ludmila sair da reunião, desligar, sair e voltar de novo.
Ok. Vou tentar então. Just a minute. You can see that now?
No, we
ainda não.
No.
Você já apresentou alguma vez, Ludmila? Só para
Já.
tentar entender o problema.
Well, Ludmila.
Para mim aparece como... Aparece aqui, apresentando, compartilhando.
Strange.
Talvez a solução seja realmente mandar o arquivo para alguém
Ok.
e essa pessoa vai trocando os slides para você.
Ok. Para quem eu posso mandar?
You can send to me, Ludmila, if you want.
Ok.
O computador às vezes surpreende a gente, né? Não dá para entender.
Milton, I sent you.
Okay. Waiting.
My connection is very bad. So...
Receive it.
You can see now?
Okay. I will share my screen, okay?
Yes, now it's working.
Yeah, okay.
Yes.
Go ahead.
Yes.
Yeah? Okay, thanks.
Ludmila, any problem? I have your presentation on my
Let's
screen
go.
if you want, okay?
Okay, thank you. Let's go again. Orchidaceae family comprises about 7% of the all angiosperms, and it's considered one of the largest families of this group. It is estimated that the family has about 24,500 species distributed worldwide, but having a greater concentration and diversity in tropical and subtropical regions. Brazil has about 2,420 species in 235 genera. Most species are epiphytic, but we also have rupicolous, terrestrial, marsh, and sapromyophytic species. The floral morphology is constant in the family. Orchid flowers have always 3 sepals and 3 petals, and one of these petals is modified and a structure named lip or labellum. And in this special petal that the floral resources are produced. Oncidine is the largest subtribe of orchids. Representatives of this group can be found throughout the American continent, with many endemic species from Brazil. They are diverse in their pollination relationship. They exhibit flower types adapted to a range of different animals, like butterflies, hummingbirds, wasps, and several kinds of bees, even male euglossum. In Oncidine, only moths and flies are accepted as pollinators. The animals explore different kinds of resources in flowers: nectar, produced in nectarine, oil in elaiophore, and fragrance in osmophore. But most species do not offer rewards to the pollen factors and attract the visitors by the sight of various forms, including the pseudocoplar syndrome, as in Tolunia henicani. This species is pollinated by males of newly emerged wasps. In relation to the reproductive system, the species of Oncidine can be self-compatible or self-incompatible. In the literature, many researchers believe that resource flowers, which receive many visits from pollinators to collect the floral resources, may be self-incompatible. And flowers without floral resources have very low visits and need to be self-compatible to ensure the fructification. In 1982, Williams, based only on morphological data, formulated two hypotheses about the evolution of floral resources and pollination in Oncidine. He believed that flowers evolved from flowers with nectar to flowers of deception without resources, and that the pollinators of the most basal groups would be pollinated by nectar-feeding bees, evolving into more specific associations, such as pollination by wasps. In my postdoctoral, I could analyze 81 Oncidine species. I performed morphology and floral anatomy studies. I applied histochemical tests for different classes of substances. I also performed chemical analysis of the fragrance to check the odor composition. I extracted, amplified, purified, and sequenced 4 regions of DNA: ITS, MATE-Key, PSBA, and YCF1. And then I was able to infer a phylogenetic hypothesis for the subtype. The morphoanatomical and histochemical analysis of the 81 species allowed to prove the wide range of floral resources that Oncidine offers to pollinators. Among them, 35% have elaiophores, secreting fixed oil for female oil-collecting bees. Almost 12% have nectaries and secrete nectar, which can serve as a food source for different groups of insects. Almost 80% present osmophores that secrete fragrance collected by male of euglossine bees. And 45% have no glands or have osmophore that secrete the odor just for attraction. And these species were considered here pollinated by the scent. Among the species that secrete oil to their pollinators, I could find 2 kinds of cells responsible for the secretion. Here are the unicellular trichomes, as these species, Fimatidium delicatum, Chitroglossa aurata, Zygostatis alleniana, and Ornithocephalus myrtico. Note that the oil is between the trichomes. Here with Sudan coloration. And a smooth palisade epidermis has in this Gomeza species. Note that you can see that some species have a shiny callus, like here in Gomeza damascenoi and in Gomeza echinata. In this species, the oil is exposed to the pollinators, and in another species, like here in Gomeza cornigera, the callus is dry. In this case, pollinators need to scrape and break the cuticle to collect the oil. As in Eliophorus, in Nectaris, there are also two kinds of cells involved in the secretion. Unicellular trichomes, as in the most species, here in Comparative coccinea, Rodriguesiopsis, Capanemia, and Rodriguez. And a smooth epidermis, as in Triseux falcata. For most species, during this investigation, I found some species with osmophores responsible for the fragrance production. However, the use of this floral fragrance, like a resource, was confirmed only for Notili species, like this. These species are pollinated by males of Euglossine bees. For the most species, no floral glands have been found, or they have osmophores that produce odor only for attraction. Chemical analyses have shown that there are no attractive compounds for Euglossine bees. In this case, these species were considered pollinated by the state. About the floral resources, what was expected? According to Wiener's hypothesis, flowers with nectar at the basin and flowers without glands in groups with more recent diversification. And it was not what we found here. Here, we have at the base of the cladogram a group with Eliophorus in red, or without resources in blue here, followed by flowers with osmophores here in yellow. Then we have a group with nectar here, followed by flowers pollinated by males of Euglossine bees, Notili species. In the most recent diversification groups, we can find flowers with Eliophorus again. We can see the flowers that produce oil and nectar have appeared several times throughout the evolutionary process. Now about the reproductive system in Osdini. What was expected? Flowers with resources would be self-incompatible, and flowers without resources would be self-compatible. Here in red, we have the species that produce some kind of resources, oil, nectar, or fragrance. And in blue, species that have no glands. The letter C indicates the self-compatible species, and the letter I indicates the self-incompatible species. If you look closely at this cladogram, you can see that the hypothesis is confirmed for most cases. Note here, species with some kind of resources tend to be self-incompatible. Here, here, here. And flowers without resources tend to be self-compatible. Here, here. About the pollination. What was expected? According to Williams, it was expected to find nectar-feeding bees at the base and wasp-pollinated flowers in the most diversified groups. But it's not what we can see here. At the base of the cladogram, we have species pollinated by small collecting oil bees, like Tetrapedia and Paratetrapedia. Wasps were recorded as pollinators only for one species of Brassia, here, and one species here of Capanema. We have a registration of pollination by hummingbirds for Rodriguesia decora, a species with red flowers and a long spur. Registered butterfly pollination for Comparative coccinea, here. And then we have a large group of flowers pollinated by large oil-gathering bees like Centris and Epicaris, both for flowers with oil or pollinated by the seed, here in blue. So, with this work, we were able to conclude that the hypothesis formulated by Williams, based only on morphological data, could not be confirmed. The use of molecular dates showed us that the evolution of the floral glands and the relationship with the pollinators are much more complex and suffered variations throughout the evolutionary process. And the theory that flowers with resources tend to be self-incompatible can be confirmed with the dates that we obtain here. That's all. Thank you for your attention and sorry for the problems.
Thank you very much, Ludmila, with this spectacular flowers in your presentation. Is there any question in the chat?
No, have no question.
No question? Here in this room? Anyone with a question?
I have one.
Okay.
One. The pollination you're mentioning, you did observations in the field in naturally occurring populations or here at the herbarium?
For some species, I go to the nature and made the observations, and another for literature.
Mm-hmm. And for the ones that you made, where was your field site?
Sorry?
Where did you do your observations?
Okay, in Serra do Japi, I studied the Comparative coccinea and 2 species of Gomeza and 2 species of Capanema. But now I can't do more visits to camp.
That's a pity. Okay, thank you, Ludmila. Beautiful work.
Thank you, Thomas.
Ludmila,
Yes.
have you detected some kind of hybridization in your work? Is it possible to detect this kind of event?
It's possible, but in the nature, I don't see any hybrid. I never see. For Oncidine, no. For another groups of orchids, it's very, very common, the hybridization, like in Epidendrum. But in Oncidine, it's very difficult to see these hybrids in nature.
And why? Do you have an idea of why it is occurring? Because it's it's quite common in Orchidaceae, and in Oncidine it's not common.
Yes, it's common, but they are very variating morphology, and this flowering in different periods. Species, it's the same morphology does not occur in the same ambients. So it's more difficult to have a hybridization in Oncidine.
Yeah, I remember a few years ago there was a paper, I guess, saying that there was a lot of hybridization in Orchidaceae.
Yes.
And do you agree with that? It's a nightmare to know species.
For the most, yes. But in this group that have specific resources for specific groups of pollinators is more difficult than orchids that have a generalist morphology. So for this small group, is more difficult to have a hybridization.
Thank you.
And what about the works of Cassio Vandenberg regarding the phylogeny of the orchids? Do you agree with the results of the Cassio and his work?
Yeah. Cassius studied another group of orchids. That group, I believe that the results are correct.
Are solid. Okay. Thank you. Any questions? Any further questions? No? Okay.
No.
Thank you, Ludmila. Thank you very much for the presentation. We are on schedule in time. So with children bouncing around and all the problems with connection, we could perform your presentation.
Okay. Sorry.
No, don't be sorry. Okay. Well, folks, with this last lecture of the Flori lecture, as Andres Gisser put in the chat, with this last lecture, we conclude the first day of our symposium. Tomorrow the program starts at 9 in the morning, 9 o'clock, with the lecture that you will give by Professor Jonathan Codd from the University of Manchester, United Kingdom. We'll talk on some physiological adaptative data in a high Arctic. Tomorrow also will be hold 6 international internship talks, with 3 of these talks in the morning and 3 after lunchtime. So let's honor the work of colleagues tomorrow. Do not forget to fulfill the form in the description of the video to get your attendance certificate. You must assign the 2 days to get the attendance certificate of the symposium, okay? So do not forget, okay? I would like to ask you a little favor. If you could open your cameras just to take a picture of this moment to put in our social media. If you could open the camera just a little bit. Okay. Hi, Talita. With a mask.
Hi.
With a mask, no. Where are you?
É isso que eu já ia perguntar. Onde que você tá, menina? Pelo amor de Deus, hein?
In my domínio. It's okay.
Okay. Good. I'm Cynthia. Stella, Vinicius here, Malu, Fernando. It's good to see you all. Okay, let's take a picture. 1, 2, 3. Say cheese. Okay, guys, thank you very much. And for all the people in the YouTube as well. Let's now rest a little bit and see you tomorrow at 9 o'clock. Okay, thank you very much for everybody, and be safe, be healthy, take a rest. Bye-bye.
Bye-bye. Thank you
Thank you,
all.
everyone.
See you later.
Bye.
See you tomorrow.
See you.
See you.
Bye bye. See you.